Hello, welcome to this video. So in this video, I'll discuss Feynman's path integral approach or path integral formulation of quantum mechanics. So this is a lot of you must have heard about this path integral, Feynman's path integral. But yeah, this video is not kind of a general discussion or a layman level discussion, a popular science kind of discussion. So there will be a lot of kind of very not really yeah, kind of advanced and very much a lot of mathematics in this video. So, and this video is personal. I mean, I'm not expecting any layman to watch this video just because, I mean, just out of interest, because this is not kind of, yeah, you can watch a video, watch my other videos in which I just discuss theory of everything and stuff just out of interest. But in this video is not that. This video is a technical video, and especially for those who want to understand this topic, because this topic is admittedly a bit difficult to understand. And I have this is actually, as you can see, a 63-page PDF which I have prepared. These are my handwritten notes, and I'm really sorry about my handwriting, as my professors and my friends are, they always say. But I know it's very but I hope you can understand, because I'll be saying it out loud. And yeah, if you're here just to understand, I think I think you can understand it, right? It's although I admit the handwriting is pretty, I mean, whatever. But yeah, so anyway, so yeah, basically in this video I'll just discuss, I will give you a basic introduction to the Feynman's formulation. And of course it's such a complex topic that even a basic introduction is gonna take a lot of time, of course. And I will derive the propagator of the Feynman path integral, as well as the basic notation of the integral, and everything I will explain and mathematically derive. And I will also show you how you can arrive at Planck's famous quantum equation E equals hf or equals h nu, using this approach, using the propagator, and also using Feynman's approach. And also how you can derive de Broglie's relation h over p equals lambda using Feynman's approach. And also how you can derive Schrodinger's equation for a free particle. That means the potential, I have assumed the potential to be zero, that's just a free particle, no forces acting on it. All of this I'll show in this video, I'll cover in this video. And also I'll cover other important the basic topics, like how to construct the sum over paths, and what exactly, how to solve the integration, how to derive the propagator for a free particle, and the multiplicative law of propagators and everything. But yeah, this video is only about the free particle, because you can of course extend this for to a more general case, that a particle with some potential field. And once you understand this video, that should not be a lot difficult, because the mathematics, the approach is same. But of course it's a bit more complicated, definitely. But all of that is not discussed in this video. This is just an introduction and for the free particle. But I still I've tried to cover a lot. So yeah, and yeah, so let's get started. Now see, as I'm just reading out from this PDF, the first few pages are just text, and after that the mathematics will start, right? So this Feynman path integral formulation is just an alternative formulation of quantum mechanics. And you may see that we already have the canonical formulation of quantum mechanics. I mean, the one we usually study in undergraduate courses. Actually, I myself am an undergraduate student, and I am also studying the canonical quantum mechanics. And path integral is not usually taught at this level. It's a bit more advanced topic, but I'm just studying it out of interest, and also as part of my UG dissertation project, the undergraduate dissertation project. Yeah, not just for the dissertation, I'm also doing this out of my own interest also. I have heard a lot about path integrals from a very young age. I mean, when I was in my high school, I mean, say 4 years back, 5 years back. And but now I'm actually learning the mathematics of path integral, and I'll discuss a lot of it in this video itself, and you'll be able to appreciate why it's a mathematically elegant and beautiful theory. I mean, yeah, we have the canonical formulation of quantum mechanics, and see, both are equivalent formulation. It's not like that is wrong and this is right. All are equally right. Yeah, maybe in some, for this kind of problem, this formulation is easier to use, easier to implement than that formulation. But yeah, fundamentally they're equivalent math, and they give me the same outcome, and all of them are right. It's not like no formulation is more right than the other. All of them are correct. Whether you're talking about the matrix mechanics, Heisenberg's formulation, or you're talking about Schrodinger's wave mechanics formulation, I mean, the usual stuff we learn in canonical formulation, this bracket notation and all this vector space, or you're talking about Feynman's formulation. It's more or less the same. I mean, they're all equally correct. But then why even learn about an alternate formulation? Why make life complicated when we already have the canonical formulation? The reason is, see, this Feynman's path integral formulation is useful in field theories and more complicated situations, like when you have a lot of particles and you want to apply the quantum mechanics. See, like I've written here, for the QM of a single particle, for quantum mechanics of a single particle, the path integral has no significant advantage over the canonical formulation. But path integral is more mathematically elegant and more important, and it's often referred to as the most important generalization in physics because the history of quantum mechanics, I mean the canonical, the conventional development of quantum mechanics, if you see, it's not like general relativity. It was not developed by a single person in a very well in a methodical manner, like Einstein developed general theory of relativity almost single-handedly. But quantum mechanics was developed by a lot of scientists. First, we saw some disagreements between experiments and classical physics, and then we felt that maybe we need some radical re-understanding of the world. And then a lot of scientists, then there was a kind of quantum mechanical, the initial theories of quantum mechanics, they were like, they challenged our very basic notions about reality, like wave particle duality and everything. And it took a lot of time, and it's kind of messy. If you see the development of quantum mechanics, the history of quantum mechanics is kind of messy, the canonical formulation, and it's not mathematical. I mean, of course it's a correct formulation, as I already told you, but it's not, it lacks that mathematical beauty. I think we'll be able to appreciate this as we go into the mathematics. So let's just do that without wasting any time here, right? So let's say particle moves from point A to point B in space-time. See, point A is a point in space-time and point B is also a point in space-time. So basically, we suppose a particle moves from a point in space to a point to a different point in space, and to do this, to accomplish this motion or whatever, I mean, there should be a concept of time. Suppose at time t equals to say t1, it was at point 1, and at time t equals to t2, it has reached point 2. So we are studying this total this part. Suppose we have fixed the initial point and the end point, and we are studying this all the different paths the particle can take. Because if this is your initial point, this is your final point, then there are a lot of, I mean, there are a lot of suppose the particle can go like this, then like this, like that, like that. There are a lot of possible paths connecting the 2 points, right? So basically, when I say a point in space-time, I basically mean, you can think of it like this. You have a two-dimensional space. Suppose on one axis, just like a xy axis, on one axis you plot the space coordinates, say x, on the other axis you plot the time coordinate t. So suppose any point on the space will be, say, x comma t or t comma x, whatever. So basically, it's you are specifying the time and the position of the particle. So suppose t1 comma x1 is a point, the initial point, and t2 comma x2 is the final point. So the t1 comma x1 point is our point A here, and point B is t2 comma x2, and we want to find and the particle moves from point A to point B, means the particle moves from x1 in position in space to x2 position in space, and the corresponding time when the particle was in x1 was t1, and when the particle is at x2, the time is t2, the corresponding time is t2. That is what we mean. And the initial points, the end points, the initial and final points, that means A and B, they are fixed. These points are fixed. In between, we are trying to find out the different paths. So yeah, it can accomplish this by many paths. Now each path contributes to the total propagator. What do I mean by propagator? I'll discuss it in mathematically, and also what is the general meaning of propagator. See, basically propagator is the total probability amplitude. Suppose this is an event A to B. We say this event A to B. That means, what is the event? Event means a change in state, right? Something is, an event has occurred. That means something has occurred. There is some change. If nothing is changing, then how can we distinguish? Then nothing has occurred essentially. So something has changed, that means something has occurred, some event has occurred. Event A to B means, that by event we are talking about the event that the particle starts at point A and reaches point B. This is the event, and this propagator from A to B is basically the probability amplitude of the event. That means it's essentially a mathematical quantity, probability amplitude, which we can associate with this event. And if we take the modulus square, if we take the absolute value of this probability amplitude or propagator and square it, that is the mod square, then we will get the probability of this event. Like, a particle can go from point A to point B. It's not like the particle will always go from point A to point B. There is a certain probability that the particle will go to point B from point A. There is some different probability that the particle might go to some other point C from point A, and all these things. So if we take the mod square of this propagator, we can find the probability of this particular event, that the particle moves from point A to point B. So that is what we mean by the propagator. And each path, so point A, connecting A and B, there are a lot of paths, and each path contributes to the total propagator. That is the total probability amplitude between these two paths, that is for this event. So we calculate the action S for all possible paths between the initial and final points. What is the action? I'll tell you right now. So yeah, we calculate the action for all possible paths, not just the classical path. I'll tell you what I mean by all this. See, so depending on this action S, all paths contribute differently to the final sum of paths. I mean, if there are a lot of possible paths, is ideally, even mathematically, there are actually infinitely many possible paths connecting A and B. Suppose A is this place and B is this point. So of course you can just directly connect them using a straight line. You can do this, that. Then suppose from A you can draw a path maybe to the end of the universe, to beyond Milky Way, and then you can again come back to B. A lot of infinitely many possibilities. We will see the mathematics of all of this, but yeah, all the paths contribute differently, because see, if a particle is moving from point A to point B, even without going into the mathematics, intuitively it's obvious. I mean, it seems likely that the particle will take the direct path, or at least a shorter path than the particle say. I mean, the probability of the particle doing this is much more than the probability of the particle maybe starting from A and going all the way to say Jupiter and then coming back to B. So the contribution of the path via Jupiter is much less than the direct path, right? So all the paths contribute differently to the final sum over paths, but we need to take into account all the paths ideally, at least at the quantum level. I mean, the contribution is not zero. That's what I'm trying to say. Because yeah, as Murray Gell-Mann famously remarked, anything not forbidden is compulsory in quantum mechanics. Quantum mechanics is essentially a theory. See, I've written there. It's a theory of possibilities and probabilities. In quantum mechanics, we have this uncertainty. We cannot define exactly. Like, see, okay, let me just. Where was I? Yeah. So the classical action is. I mean, it's actually the classical action. It's minimum, not maximum. Okay, it's actually minimum. So the classical path has the maximum contribution. I'll explain why. What do I mean? Because minima means that if S is the classical action, then if S is a minima, then the first order derivative, or if I say delta S, a small change in S will be 0. And that means it will have the maximum contribution. I'll tell you why. But what do I mean by classical action? What is action in the first place? See, I'll tell you. Okay. I'm coming back to this point right now, but before that, let me just discuss what I mean by action. Okay. Yeah. Yeah, see, the kernel is nothing but the propagator. They are just kind of interchangeable terms. So k, b, comma a is the notation for the kernel, and this is actually the propagator from A to B. So in the notation, we first write the final point and then we write the initial point. So b, comma a does not mean b to a, it actually means A to B. If it was b to a, if the initial point was b and the final point was A, we would have written k, a, comma b, right? So the kernel k, b, comma a is the sum of all the paths or trajectories from A to B with a contribution from each path. So essentially it's the total probability amplitude from A to B, right? So classically, in classical physics, say at the level of Newtonian mechanics, suppose you have a ball or a car or whatever, we can exactly determine the potential energy and the kinetic energy of the particle. This T is the kinetic energy and P is the potential and V is the potential energy. And the Lagrangian of a particle is defined as this difference, T minus V, kinetic energy minus potential energy. So classically, since we can definitely determine the T and V, we can know exactly determine the Lagrangian of a particle in classical physics. So classically, we have a well-defined unique action S, and this is the classical action. And action is defined by this time integral of this of the Lagrangian L. L is T minus V, and if we take the integration from Ta to Tb of L dt, I mean the integration over time, T is the variation of, I mean the integration variable here, the variable, and the limits Ta Tb means see, this particle is moving from A to B. So say when the particle is at point T, the corresponding time is Ta, and the particle is at point B, corresponding time is Tb. That's why the integration limit is Ta to Tb. So this integration is how we define the action, right? And Ta Tb at the initial and final points, which we know, and L is T minus V, which is the Lagrangian, and this is the action. So T, the kinetic energy is classically it's half mv square. So there is a velocity term here. Then in potential energy, it depends on the position, and of course, ideally there can also be a dependence on time. So this Lagrangian L is a function of position, velocity, and time. But here we denote it like this: x dot, and t. X is position, x dot is velocity, t is time. Here actually we deal with generalized position and generalized velocity. So basically we in Newton's theory, we just deal with v, velocity. Here this notation actually there's a different concept. It's a slightly more generalized concept. In the Lagrangian formulation and Hamiltonian formulation of in classical physics only, we use generalized coordinates, not the usual, not any fixed rigid coordinate system like Cartesian coordinate or maybe whatever. We use a generalized coordinate system. I mean, and there the coordinates are generalized. This x is actually a generalized coordinate, and x dot is a generalized velocity. Now I'll not go deep into this here because this is a topic of classical mechanics. I mean, that is not of our concern here. And yeah, if I go deep into everything, then this video will never end, kind of. Yeah, right. So yeah, now basically the action, that means this S equals integral L dt. This action describes how the balance of kinetic versus potential energy of a physical system changes with time. See, the L term is contains the T and V potential and kinetic energies, and you are integrating it over time. That means it's a time integral. You are kind of seeing how this Lagrangian, or in turn how kinetic and potential energy, and how the balance between kinetic and potential energy, how this changes with time. Roughly from this equation right here, you can see that the action, that is what the action describes. That is what is the meaning of the action. And the action just describes the trajectory of the particle. The trajectory of the particle depends on the Lagrangian and everything, right? It depends on time, it depends on the position, and it depends on the velocity also, right? So for a particle of mass m subject to potential v, L is mx dot square over 2, because its kinetic energy is half mv square, or mv square by 2, and since generalized velocity v, we are using v, we are denoting by x dot, so mx dot square over 2 minus potential energy v, and here we have assumed, in the most general case, we have assumed a time varying potential, that is the potential is a function of position x as well as time t. Whatever, this is just a general form of the Lagrangian, we will not be using it directly, so no worries. Now classically we only have a single trajectory, single path, because classically we can determine this t and v, mx dot square by 2 and as well as v, so we can determine L directly, and since the integration limits are also known, so we can determine the action for classical action, and that is why in classical physics, in Newton's, using Newton's, so you can actually precisely predict the trajectory of a football, of a car, of any macroscopic body. In Newton's theory, it doesn't say that okay, the probability of the particle following this path is this much, and the probability of the particle following that path is that much. That is not true in classical physics, because in classical physics we have only a single trajectory. And yeah, this is actually called the principle of least action, because every particle tends to follow the path that minimizes the action. Okay, so that means this action s equals integral L dt, this action will be minimum. It should be the minima. If you see the trajectory, I mean not this trajectory, even it's kind of the particle can follow a lot of trajectory, but it will follow that particular trajectory for which the action is the minimum. This is called the principle of least action. Like yeah, this is a very fundamental principle actually. Particles will always tend to follow this path. But in quantum mechanics, I'm not going deep into the classical action and everything, okay? But yeah, so in quantum mechanics, in QM, all paths contribute equally but at different phases. I mean, they do not actually contribute equally. The wording is not entirely correct here. But yeah, in quantum mechanics, all paths have some contribution. It's not like there is a single path. So all paths contribute between points A and B. And the phase of the contribution for a given path is the action S. It depends on the action S for that path in units of h bar. H bar is basically, you must have heard of h, which is Planck's constant, and h, if I divide h over 2 pi, that is the reduced Planck's constant, that's h bar. So when I say action is in units of h bar, whenever you're expressing something in units of something else, basically what I mean is that s divided by h bar, right? Suppose if this amount of s corresponds to this, if 1 h bar corresponds to this s, so if I divide by h bar, I mean if h bar corresponds to this s, then 1 in units of h bar, 1 will correspond to, if I divide by h bar, s over h bar, right? So this s divided by h bar, or some people also say it h cut, whatever, I don't care, it's a reduced Planck's constant, whatever you call it, I will stick with h bar, okay? So s over h bar is the phase of the contribution of each path, and it's different for different paths, because for different paths the action s is different. H bar is a constant, but action s is different for different paths, because s depends on the Lagrangian, and the Lagrangian depends on the position as well as the velocity x dot as well as time, so it's different for different paths. Now the kernel k b comma a is the sum of contributions. We have just denoted it by c. You can denote it by phi also in some. Actually, I have followed the book called Feynman Hibbs. It's a book written by Feynman himself, the master himself, and Hibbs. So in Feynman Hibbs, what I found was that in general, I'm saying that it's a very well written book, of course, but and it's one of the classic texts on path integrals. But the mathematical derivations, there is a lot of step jumps, so it's pretty difficult to follow at undergraduate level. But in my video, in this PDF, I have actually for the last 1 month I've prepared this PDF using Feynman Hibbs, as well as I will explain everything. I mean, I have no step jumps or anything. So anyway, so the contributions of each path, yeah, it's a sum of all the contributions from all the paths. That is the kernel basically. And the contribution of each path C, it has a phase proportional to the corresponding action. That means I told you phase is S over H bar. So C is actually A, E, or the exponent, it's E means the Euler's number, that is E raised to the power of, that is exponential, I S over H bar, where I is the imaginary number and S over H bar is the phase. and this a is kind of the proportionality constant, you can say, or later we will see that this is actually the normal. It's no, this a is not that a, but yeah, anyway, it's a kind of proportionality constant. It roughly translates to the amplitude, kind of. Okay, and it also makes, yeah, it's kind of, it makes sure that the kernel is normalized, because to describe a physical system, like normalization, basic idea you should have even in canonical quantum mechanics, like the probability of finding a particle between in all of space, like if we're integrating between minus infinity to plus infinity, we must find the particle somewhere in space. So in that case, the integration from minus infinity to plus infinity of mod psi squared dx is 1. This is what we assume, where psi is also the probability amplitude. It's not the kernel, it's the wave function, but it's also a probability amplitude term. And like I said, the mod square of this probability amplitude will give you the probability of finding the particle at that position in space and in that point of time. Psi is a function of x and t, right? So what is the meaning of integration minus infinity to infinity psi x comma t dx equals to 1? That means you are integrating over all of space, and then the probability of finding the particle must be 1, because you must find the particle somewhere in space. So if your wave function is such that it does not satisfy this integration, I mean if you solve the integration and you do not get 1, you get something other than 1, that means your wave function is not normalized. It cannot describe a physical system. Then you have to make the wave function normalized, and then maybe you have to multiply it with some constant, and that is what we call the normalization constant, the basic idea, right? Now, contribution of each path of an individual path is a e to the I s over h bar, where s is the action of that path, and e to the ix is cos x plus I sin x, right? All as famous identity, which we learn in complex theory, complex number theory, very basic complex number theory. I is the imaginary number, under root of minus 1. So similarly, a e to the I s over h bar can be written as a cos s over h bar plus I a sin s over h bar. It's basically, you can see, s over h bar is the phase of the sinusoidal waves, the cos wave and the sine wave. It's in the bracket, you see, in the sine term and in the cos term. And a is kind of the amplitude of the sinusoidal wave. I told you it takes care of the normalization. And s over h bar is the phase, which differs for all paths, because the action s depends on x dot and t, which is different for different paths, of course. I discussed previously. So see, in the classical limit, I mean if the action s is huge as compared to h bar, because h bar is anyway a very small number, Planck's constant, it's of the order of 10 to the minus 34, right? And here you're dividing by 2 pi, but the order is the same. So if the action is huge, that means for if x is, I mean for day-to-day life, for macroscopic objects, right, for big objects, for classical objects, that is why it's called the classical limit. S is much greater than h bar. So in that case, you see, s over h bar is very large, because s is a huge number and h bar is a very small number. So s divided by h bar is a very large number in this case, if s is much greater than h bar. That means the phase is very large. S over h bar is the phase, right? That means if we move a path by a very small, phase is very large means basically the frequency is very large. Suppose it's not, the wave is not like this, it's not like this, it's like this, kind of. That means if we move a path by a very, roughly speaking, if we move a path by a very small amount on the classical scale, the change in s is also negligible. You see what I'm trying to see? Okay, let me just show you. Okay, if I just let me just show you, if I just use the Desmos graphing calculator. Okay, let me just show you, yeah. Desmos, okay, open graphing calculator. So since we're doing this, I think this will give a good understanding. Suppose I plot sine x, we get this kind of graph. So x is the argument of the sine function. If I increase this, suppose if I plot sine 100x or 10x, you see the graph has become so much more, I mean kind of it's like this. You can see the graph. If I do just sine x, it's kind of more spaced out, right? So similarly here, what we're doing is that, you see this equation, you see in the same for cos also. If I say let me show you, if I do cos x, this is the thing, and if I do cos 10x, this is the thing, same thing. I mean the cos and sine both are sinusoidal curves. The nature is the same. They're just shifted, translated by a constant. But yeah, so cos s over h bar and sine s over h bar. So if this s over h bar is increasing, that means the wave is becoming, I mean from here it's becoming like this, like I showed you. And this a is the amplitude, kind of this a is fixed, because see, this a is a constant. Suppose I multiply this by what, say 10 or maybe say 2. That means this will lie between minus 2 to plus 2. I mean just look at the endpoints. Just look at this up limit. It's all the maximum. It's reaching up to plus 2, and it's up to, and below it's up to minus 2. It will never come down below minus 2, and it will never go above plus 2. So we are just changing the phase, say 10x or 5x, whatever. But this a is constant. That means this amplitude is constant, right? So I think I showed you visually what is meant by this equation, right? But now if this phase s over h bar is very large, in the classical limit it is very large obviously. But then if we move a path by a very small amount on the classical scale, that means the s is changing by a very small amount, the action, right? Because we were moving a path by a very small amount. So in the classical scale, the change in s is also negligible, but in the quantum scale, because in quantum scale means in units of h bar, even a small change in s corresponds to a significant change in the path. See what I mean by this is that, okay, suppose on a classical scale, suppose what is the difference between 1001 and 1000, these two numbers, these both of them are huge numbers. So the classical scale, the difference is just 1, 1001 minus 1000 is 1, which is okay, just 1, it's a small number. Now if we divide both of them via, see in here we are dividing s by h bar, which is a very small number, 10 to the minus 34. Suppose we divide both of these numbers, 1001 and 1000, by this small number, it's there are say 8 zeros, 10 to the minus 9 something or 8. It's still a huge number as compared to Planck's constant, but still if we divide this by this number 0.00000000001, let's do this. Calculator. Okay, so first of all let's just divide 1001 divided by 0.000000001. We get this number. Okay, just let me just copy it. Okay, why can't I copy it? Just a second. Yeah, copy. Fine. Now 1000 divided by 0.0000000 what 1 2 3 4, yeah, 1. This number I'm getting. So what is the difference between the this minus, I mean actually we should have done that minus this, but anyway we'll just get the result in negative. This minus the number we have copied. So this is the so if you just ignore the minus sign, because we have done it in done the calculation in the reverse direction, but then we get the difference now is, you can see the difference is, it's a huge number. You see this, the difference, it's a huge number. On the classical scale, 1001 minus 1000 is just 1. But if I divide both of this number by this small number, then and then take the difference, then that means kind of here if you divide both of these numbers by h bar and then take the difference, then on a quantum scale the difference is a huge number. That is I think now you are convinced, right? Yeah. So we will get a huge, yeah. So thus a small change in s corresponds to a large change in s over h bar, the phase. That means the sinusoidal waves they vary rapidly between positive and negative values, because a sinusoidal wave means it's oscillating, it will up and down. But if they're varying, if they're changing between positive and negative values very kind of rapidly, then what happens is that the net contribution is 0 in the classical limit, because if one path makes a positive contribution, then another path which is very near to it, infinitesimally close to it, will make an equal but negative contribution. Like if I make this phase very high, suppose cos 5x, if I make it cos 5000x, you see, you cannot even distinguish. They are so near. Like if I zoom in, then also I guess you will not be able to distinguish. I mean, they're very near. I think there's a limit to Desmos. But yeah, now I think you can distinguish. I have zoomed in a lot. See, they're so close together. This path has a positive contribution, but very near to it is a negative contribution. So that means the net contribution will be 0 in the classical limit. I mean, only then we can approximate the phase to be very high. Otherwise, not. So since the classical action S is the minimum, but yeah, what about the classical path which I was talking about? The classical action S is the minimum. That means we just said that since it's a minima, small change in the path does not give rise to any change in S by definition, because it's a minimum. And you see delta S is 0. That means delta. That means since for the classical path, it's a special path. For the classical path, since we get since a small change in this classical path does not give rise to any change in the action S, delta S is 0, that means for this classical path we get a net contribution that cannot be neglected, because even we are changing this path, we are not getting any change in action, so we will get, there is nothing to cancel this path is alone. So in the classical limit, if S is much greater as compared to h bar, only the classical path survives. The other paths cancel out, they are almost 0, they can be safely neglected. And that is why you see in at the classical level, Newton's laws work. We don't need to, when you're calculating the velocity of a car, a car moving from point A to point B, we don't need to consider the path integral of the car all the different paths and everything, because a car is a huge body. For it, the classical path is the only. Even if we do the path integral, we will see that the ultimate other paths will cancel out. So this is the beauty of path integrals. You see, Feynman, it's a general theory. You can derive the classical results from it, but in general, but at the quantum level, see, for the classical path, we get a net contribution that cannot be, and yeah, thus in the classical limit, only the expected classical path is considered. The world we see around us at the classical level, it's just the most likely outcome of a more fundamental, more general world, which is described by Feynman's path integrals. But at the quantum level, when S is not much higher than H bar, then of course, as I already told you, when S may be comparable to H bar, then we cannot ignore the other paths. We need to take into account all the paths. Now let me just show this part. I will cover everything. Okay, I know I'm moving because these notes have been prepared over 1 month and not really organized. But yeah, I'll cover everything. But since I'm talking about the classical limit, let me just speak about this a bit at this point. Okay, this was in after this, I guess. Okay. Yeah. See, in classical mechanics, a particle follows a fixed trajectory, classical action, least action. But in quantum mechanics, there are many possibilities, and it's totally probabilistic, right? And there's this thing called the probability amplitude, and every particle starting at point A has a finite probability amplitude of reaching point B, and this is denoted by k, b, comma a. I already told everything, kernel of the propagator, and the mod square of this kernel will give the probability or probability density for the particle reaching B from A, for the event A to B, or whatever you say. I already discussed this near the beginning of this video. So Feynman postulated that the propagator k, b, comma a can be calculated by adding up complex numbers. I already told you this, right? The contribution of each path is some constant times this thing, e raised to the power I s over h bar. That is what I've written here, right? So the propagator can be calculated by adding up the complex numbers e I s over h bar for all possible paths or actions between the points A and B. That means k, b, comma is proportional to this thing. Say e raised to the power I over h bar s0 plus e raised to the power I over h bar s1, and so on. I mean, here 0, 1 have no special meaning. They just indicate the different path. The first path is 0, is denoted by 0. The second path is denoted by 1, and that's all. So basically all e raised to the power I over h bar sj, where j runs from 0 to whatever, how many paths are there. So they are all vectors kind of. Because see, e to the ix is cos x plus I sin x. And yeah, anyway, we can also write it as a complex number. It's a polar representation of a complex number, and on the complex plane, like this is the real line and that is the complex axis, the real number line and the complex number line, imaginary axis. Well, any complex number or any, I mean, you can express it in polar form or Cartesian form, doesn't matter, but you can, that is basically a point in this plane, and if you join the origin to that point, then you get a vector. I mean, you can associate a vector to each e raised to the power ix, or here e raised to the power is over h bar. You can do that, right? So there are vectors or arrows in the complex two-dimensional complex plane, and they make angles sj over h bar, phase. This phase is the angle, right? E to the I theta is cos theta plus I sin theta. So this theta is the angle. That means if you just polar representation, if we just do these things we do in basic complex analysis, right? So this is the phase. So they make this angle with the x-axis of the horizontal axis. So the sum of our paths can be qualitatively understood as the sum of vectors. I mean, this is just to make you understand, right? It's not actually this exactly same, but yeah. So consider this diagram which you can see here, the case 1. So when the angles are varying widely, I mean the angles are varying they're widely different. So in such cases the resultant displacement is small. Angles means the phase, s over h bar. So if the phase is varying widely, like in the classical limit you see, suppose you see we start with this vector a, I mean from O to A, this first vector. Just try to see where I'm moving my cursor. I hope it's visible, right? This vector. It's making an angle theta 1. Now A to B, this vector, you see this theta 2, it's a huge change in angle. Then theta 3, B to C. Then C to 4, C to D, it's theta 4. It's a huge change in, I mean the angles of the faces are varying hugely, right? D, and from D to E, it's theta 5. But you see now we started from O and we end up at E. So the net displacement from O to E is just this small, the net displacement. So see, these angles are varying widely. Theta 1, theta 2 is this much. It's like, you can see, right? It's like this, then this, and all. It's varying widely. but the ultimate displacement OE is resultant vector is not very large in magnitude. So that means in this case the contribution of such paths is less. So that is what I told you in the classical limit, when S over H bar is very large, that then the contribution of the other paths, all the paths except the classical path are very less, because the angles are varying widely. I gave you a kind of different viewpoint using this Desmos and everything, but yeah, it's the same thing. See, this is just a sinusoidal representation, but yeah, anyway, if the phase is varying widely, then this is kind of a, if you're assuming this to be in vector, to be vectors on the complex plane, then this way also you can understand, you get the same result. I mean, just for better visualization purpose, for better understanding. And case 2, if the angles are nearly equal, then the magnitude of the resultant vector is significant or large. This corresponds to the phase is not changing much. That means the quantum, I mean, not the classical limit. So in general, when S is comparable to H bar, when S is not much greater than H bar, in that case you need to take into account all the paths. I mean, the contribution of these paths is not negligible. So you can see here, O to A, this vector you see, O1 is the angle, then A to this point, the angle is O2. See, angle is theta 1. So see, theta 1 and theta 2, there is not much change, just a little change. Then theta 3, again not much change in angle. And the net displacement, see, O to A, then this point, and finally you reach here. Actually, this I should have named it something else, but anyway, you get the idea, right? So the net displacement vector, this OA, assume this point to be A prime and this point to be A double prime maybe. So this net vector, it's a huge displacement vector, you cannot ignore it, right? So case 2 corresponds to the path that vary only slightly or negligibly from the least or classical path, because first order derivative or slight variations about the least path are minimized 0, right? So thus the classical path and those differing only slightly from it, they contribute most to the propagator. And the paths which differ very much from the classical path, I mean for widely varying angles, as I showed you, the net contribution is small. Not always negligible, but very small. Okay, so yeah, I'm coming to this part. I'm coming later. So I completed my discussion of the classical limit and how the classical world emerges from the quantum world. Okay, now let's move on to this, what I was telling you. So the probability amplitudes of all the paths are added, not the probabilities themselves. This is the basic idea of behind the superposition principle, which we already also use in waves. Even in classical wave theory we also use, but yeah, in quantum theory also the similar principle holds, and that is called the superposition principle. See, quantum theory, even the canonical formulation, the mathematics is based on linear algebra and vector space. So yeah, linear superposition. Suppose if you have a solution to Schrödinger's equation, and if you have two solutions to Schrödinger's equation, two valid solutions, then a linear combination of those two solutions will also be a solution. We use this concept everywhere, linear combination of vectors and all in vector space and everything. So whether they form a basis or not and everything. But anyway, those are a topic for a different video maybe. I mean, they are not directly relevant right now for in our discussion of path integrals. But yeah, the probability amplitudes of all the paths are added. I mean, we add the probability amplitude in superposition principle and not the probability themselves. I'll tell you the difference. See, to every event A to B, that is a change from state A to state B, we can assign a complex number. See, in canonical quantum notation, in bracket notation, we write like this, BA. And this is basically an inner product. It's kind of an extension of dot product, a more general form of dot product for complex numbers, you can say. You can calculate the inner product using using Hermitian conjugate and row matrix and column matrix. I'm not going into that. But yeah, in our discussion, it's you can also think of it like the kernel K, B, comma A. It's basically this probability amplitude. So we can assign a complex number to every event A comma B, and you can denote it like this, B inner product of B, I mean B A like this. So A is the initial point, which is initial point, and B is the final point. So we write B first and A later. This is the convention. Such that the mod square of this is the probability of the event A to B. And this thing is called the probability amplitude. See, B A, this thing. So this is according to the superposition principle, probability amplitudes satisfy the relation this BA is sum over K, the inner product of B and CK multiplied by the inner product of CK and A. So basically we are just introducing an arbitrary C in between B and A and just kind of breaking this into two parts, and then we're writing this, right? And K runs over the size of an arbitrary observable See, observable operators, these canonical quantum mechanics, these concepts I'll not be going into in this video. Basically, spectrum size of an observable means C is the kind of observable. Say C could be momentum. So if I make a measurement of momentum, then how many different outcomes can I get? Say n number of outcomes. That means n is the size of C. So that means K will run from 1 to n. So see, but in this case, in the superposition principle, we don't actually physically make any measurement on C. We just know A to B, but yes, this is just a mathematical kind of technique. Mathematically, we can write it like this superposition principle, and this actually, using the superposition principle, we can reduce the information needed to calculate this thing, and we need to calculate this thing if you want to find the probability, right? So that is the superposition principle. But if we make a, but yeah, in this case, we just measure A and B, the initial states, because we know A and B, we know the initial point and the final point, and we are trying to find out the paths in between. So, but we are not actually making a physical measurement in between, and only then this superposition principle will hold. So basically, if you look here, we are just taking a sum of the probability amplitudes, is sum of the amplitude, and after this sum, then we are taking the mod square, right? But if we actually make a physical measurement of an intermediate state C between A and B, then we have a composite event. That means a collection of two events, first A to C and then C to B. But in this case, the superposition principle will not hold, and here we have BA mod square is summation K, this thing mod square. So here we are taking the sum of the mod square. First we are taking the mod square, the probabilities, and we are taking the sum of the probabilities. But in this case, we are taking the amplitudes and taking the sum of the amplitudes, and finally we are taking the mod square of the sum of the probability amplitude. So here we are summing over the amplitudes, and here it's a sum of the probabilities themselves. So in the first case, we've considered the sum of amplitudes and the mod square, whatever. Note that the probability amplitude is the solution of the Schrodinger equation, which is a completely deterministic equation. Schrodinger equation is basically the quantum mechanical, the main equation in quantum mechanics. It describes, just like in Newtonian mechanics, F equals to ma describes the time evolution of a particle. Like if I know the position of a particle, the moment of a particle, and all of this, and the required information, the mass of the particle, then using Newton's law of motion, I can predict the trajectory of a particle. Similarly, if I know the wave function of a particle or the probability amplitude of a particle at some point in space and time, using Schrodinger's equation, I can calculate the probability that I will find the particle in some other point in space time. So why I say that the Schrodinger equation is completely deterministic. See, quantum theory itself is a probabilistic theory. It will only give us the probability. Suppose I find that the probability of finding a particle at this point in space-time is say P1. Then if the system is not subjected to any external disturbance, if nothing is changing in the system, then even if I measure the probability in the same point at any point of time, after 10 hours, after 10 days, whatever, I will get the same probability. So this is what I mean by deterministic equation. If I am not disturbing the system in any manner, then the probability of finding the particle at a point does not change. The probability does not change, but that does not mean that I can actually predict when I will find the particle in this point. See, before I make a measurement, I don't know where the particle is. I only know the probabilities. Okay, these are the possible positions I can find the particle in, and the probability of finding a particle at this position is say 20%, at that position is 30%, at the other position is say 40%, and at the probability of finding a particle at this position is say 10%. So total 100%. This I can find out, I can say for sure. But when I make a measurement at the same position, suppose at this position, I may or may not find the particle. That I cannot say. If I toss a coin, I can definitely say that the outcome of getting a head is 50% and the outcome of getting a tail is also 50%. And this is always true regardless of anything for an unbiased coin. But when I'm tossing a coin, I cannot predict whether I will get a head or tail in this particular throw, right? In this particular toss. So the same here. But by itself, the Schrodinger equation is a deterministic equation. But yeah, like I said, the mod square of this amplitude only gives the Schrodinger equation gives the solution to the wave function psi. And once we know psi, then we can take the mod square and we can find the probability. But this only gives the probability of an outcome. We cannot definitely predict whether or when we will get that outcome. Right? This thing is very crucial. This concept. Now, and here is an interesting, kind of illustration of the two scenarios. First is where we are not making any physical, where the superposition principle holds, and the second case is where this superposition is destroyed. So see, if we have an alpha particle A and any other nucleus, that means anything other than an alpha particle B, then the probability that A ends up at position 1 and B ends up at position 2. Suppose A and B collide, and suppose A ends up here position 1, B ends up here position 2. So what is the probability? If they collide, they can end up at different position. But what is the probability that the A ends up at position 1 and B at position 2 after the collide? Then this probability, to find out, we can just take the sum of the individual probabilities, because this corresponds to the second case, not the superposition principle case. Because here we can distinguish A and B, exclusive alternatives. But if B is also an alpha particle, suppose if two alpha particles collide and they end up, then we cannot say that which alpha particle. Suppose this is alpha particle or alpha particle, they collide and this particle end up here, this here. But even if this particle end up here and that there, I mean, if it's the other way around, you cannot say it, because you cannot distinguish. All alpha particles are equal, are identical. All electrons are identical. So in that case, we have to take the mod square of the sum of. First we need to take the sum of the probability amplitudes, and then we need to take the mod square to find the probability. So this is the interfering alternatives. See, in the famous double slit experiment with electrons, this double slit experiment is probably one of the most important experiments in physics, right? This first gave us a hint to the wave nature of light. But yeah, but that was a double slit experiment with light. But yeah, this has been done with electrons also, and many in ordinary matter also. And we found that this this is how we this wave nature of particles was also kind of, we got a hint about that. So basically the double slit experiment with electrons, see, if we put detectors, say light before the slit, suppose there are two slits and we are firing electrons one by one using an electron gun or something, and there is this huge screen at the end behind the two slits. So we expect to see two distinct patterns just behind the, suppose whenever an electron is hitting the final screen, we will get a spot there. So classically we expect that there should be a maximum number of spots if the electron was just a rigid particle, and if the electron absolutely had no wave nature, we expect that there should be the maximum number of spots should be directly behind the two slits, like here a collection of spots and here a collection of spots. But we see that we actually get an interference pattern with the same pattern which was observed by light in wave optics experiment. That means the electron must have a wave nature, because otherwise how it's only two waves, if they interfere, can they produce this pattern? But how is it interfering if it's a particle? But if we try to find out, suppose I throw an electron, there is no way to determine whether the electron moves through slit 1 or slit 2. That is the thing. I always get the interference pattern if I do not make any intermediate measurement. I get the interference. I get this superposition principle holds because it's a wave, right? But if I try to find out which slit the electron passes through, if I try to measure it, that means we are trying to make an intermediate measurement. That is, we put some detector, say light, before the slits. That means if an electron is passing through this slit, that means then the detector will, if electron collides with light, with a photon of light, because in quantum theory light is also has a particle nature, then we will get our detector will just kind of detect. It will light up, and we will see that, okay, so there is an electron which passed through slit 1, right? But if we set up the light, then what happens is that the interference pattern is destroyed. We no longer get an interference pattern because the superposition principle no longer holds. We are making a physical measurement in between. And again, it's a sum of probabilities as we expect classically. Now, and we cannot weaken the light, because if I say that, okay, let me use a very weak light, so to reduce the effect of light on the electron, we cannot do that, because see, weaken the light means what? To be able to detect electrons are by very small particles, right? That means the light should have a very small wavelength to be able to probe the electronic distance, electronic dimension, and that means small wavelength means a huge energy. So so the minimum amount of energy detector must have the detector to be able to detect electron. Otherwise, we will not be able to detect. But in that case, see, if we try to weaken the light, we can reduce the number of photons. But to tell which slit the electron passes through, a light of energy hf, where h is Planck's constant, hf is the frequency. That means a single photon must collide and must scatter the electron. Otherwise, only then we can detect the electron. We cannot see it with our naked eyes, right? So if we use high wavelength or low energy light, then it cannot detect something as small as an electron. And if we use a high energy or low wavelength light, which we must use to be able to detect, then the interference pattern is getting destroyed. Now, there is an alternative statement of the Heisenberg's uncertainty principle, which I have referred to here as HUP. This is given in Feynman-Hibb's book also. So, like I said, uncertainty principle says that we cannot simultaneously measure the position and momentum, both the position and momentum of a particle with 100% accuracy, because position and momentum are canonically conjugate variables. There are more other pairs also, like energy and time. So basically, if we try to measure the position very accurately, that means you have to shine light on it, high energy light, to be able to detect, to be able to exactly pinpoint the location, to be able to probe smaller and smaller distances. But shining high energy light means your light is a form of energy basically. That means you are also kind of providing energy to the particle whose position you are trying to determine. That means you are playing with, you are changing the momentum of the particle. That means if you try to increase your accuracy in your position measurement, you are compromising with with accuracy in your momentum measurement, and vice versa. So, an alternative statement is that any determination of the alternative taken by a process capable of following more than one alternative destroys the interference between alternatives. Like if we want to determine which state the electron passes through, we need to know the exact position of both the slates. On the slate screen, suppose there is this slate screen and there are two slates. You see from the side, like this is a slit. I mean, this is a screen. From the side view of the screen, not this is a screen. Suppose this is the electrons are coming like this. There are two slits, so you are seeing it from this angle, right? This is a screen. So suppose the slits are like this, the here, top and bottom. Here is one slit, here is the second slit, or whatever, like this. You can consider whatever. So basically, you want to find out which state the electron went through, the electron came from, right? To do that, first of all, you need to know the exact position of both the slates. Otherwise, you will not be able to predict. Then, suppose we assume that you can see this here, right? I've written this here. Okay, let me just zoom in a bit. Yeah. Suppose we assume that this slit screen, the screen on which the slits are present, suppose we assume that it is free to move vertically. So if an electron is coming and kind of passing through this slit and being passing through this slit, so when it is moving like this, it is kind of there is a change in the vertical component of its momentum. And since this screen is free to move vertically, because the screen is free to move vertically, there will be a recoil momentum of the screen also. Suppose the electron moves like this, so the screen will kind of come down a little. Now suppose we can measure the velocity of this screen exactly, and we know the mass of the screen. So we can measure the momentum of the change in momentum of the screen exactly. So we know momentum. But then we also need to know the position of the slits also, because only then we can suppose see, this is the slit screen and then we have a final screen. So this is slit 1, this is slit 2. So if the electron is coming from slit 1, suppose we have fixed a point in the final screen. So if the electron is coming from slit 1 to that point and coming from slit 2 to that point, in both the cases the angles are different because the point is fixed in the final screen, and slit 1 and slit 2, they are at different positions. The angles are different in both the cases. That means the electrons, the change in the momentum will also be different. So that is what I've written here. But if we measure only this momentum accurately, we still would not be able to predict the slit the electron came from. To do that, we further need to know the exact position of the slits. But then this violates Heisenberg's uncertainty principle. That means if we assume that, okay, we can, if we don't know the exact position of the slit, then how can we say which slit the electron came from? We need to know the position of the slit also, exact position. But that means to be able to tell that which slit the electron came from without destroying the I mean to be able to tell this, that means we need to know both the position and momentum accurately. But that violates the uncertainty principle. So if the uncertainty principle is correct, which we know is correct, then that means we cannot actually tell which slit the electron came from. If we want to find out, then we destroy the interference pattern. So that is why this is the kind of alternative statement of the uncertainty principle, that any attempt to determine the alternative taken by a process capable of following more than one alternative destroys the interference between alternatives. See, it's good to think about. Like you can say, oh, we already have the usual way of Feynman of uncertainty principle, delta x delta p x equals to, I mean, greater than equal to h bar over 2. So why this alternative statement? Because see, if we can describe the same principle, same phenomena by a lot of equivalent mathematical statements, that according to Feynman, that means the universe must be simple fundamentally. That means it should point at something deeper. There must be some deeper theory from which all of these different but equivalent explanations are emergent. Like quantum mechanics, Feynman path integral is a valid approach to study quantum mechanics. The canonical approach is also a valid approach, but they are describing the same theory basically. I mean the same kind of phenomena basically. Right. So yeah. See, we detect the electrons from a fixed position. So I've just mentioned all of this, right? The change in momentum in addition was another position. Fine. Yeah. Now from here I've already discussed for the next 2 pages, I guess, right? Yeah. All of this I've discussed. That's just the classical limit part. Okay. The phase and everything. You can just see the writing I just discussed previously. Okay, now let's move on to constructing the sum. Now we have a basic understanding of the concept and the approach of Feynman path integral. Now we will do a little more advanced mathematics. We'll do the actual path integral now, right now. So say a particle travels from point A to B. First we choose a subset of all paths. Now uh, basically we divide the independent variable, which is time, into equal discrete time steps of equal width epsilon. Let me show you this figure. You see, here along the horizontal axis I have plotted the position variable x, and here I have plotted time. So you see, I have divided time into discrete steps. See, this is 0 to 1, this length is epsilon. It's a time step, a discrete time length, time interval epsilon. 1 to 2 is also epsilon, the equally spaced. Okay, 1 to 2 epsilon, then 2 to 3, 3 to 4. I have not shown everything. Ultimately, up to n minus 1, then n minus 1 to n. This is what I mean by this. Okay, so this gives us a set of values ti, that means t1, t2 and everything, spaced epsilon apart between ta and tb. Ta is the initial point and tb is the final point, or you can say t0 and tn if you want to in this figure basically ta is corresponds to t0, the first initial point, and tb corresponds to tn, and 1 to n minus 1, all of these are the intermediate ti's. T and TB, or equivalently T0 and Tn, they are fixed. The endpoints are fixed, as I told you already. Now at each Ti, we choose some xi, that means some corresponding position in the x versus t space. I showed you the graph, right? And we construct a path by connecting all the points so selected with straight lines. We can define a sum over all paths constructed in this manner by taking a multiple integral over all values for xi for I between 1 and n minus 1. Okay, so basically what this means is that suppose this is a point A and corresponding time is t0 or ta, whatever you define. Then next if I along the time axis, if I move epsilon distance, I reach this level 1. So this is t1, or let's say t1. So let us choose a corresponding x1, say this part corresponding to t1, we choose a corresponding x1. Then for t2 we choose some x2, and so on. For tn minus 1 we choose some xn minus 1, and for tn it's always b, because this is fixed, right? So then now if I join all of these points, intermediate points, using straight lines like a to x1, x1 to x2, and so on, then xn minus 1 to b. So this is a path we get. But x1 is we just chose x1, and then there are a lot of possible values of x1, right? So for some at the same level 1, if for a different x coordinate, say x1 prime, and then similarly x2 prime and xn minus 1 prime, we get a second path, this path which my cursor is tracing. Similarly for x1 double prime, x2 double prime, and so on until xn minus 1 double prime, we get this third path, and fourth for x1 triple prime, and so on. Just 4 paths have been shown here, otherwise the figure would be untidy. But yeah, this is the idea, this is how we can do it. So like this we can define a sum, and we can define a sum over all the paths using so this is just one path, and like this we have defined we can define a lot of paths. So we can define a sum over all the paths constructed in this manner by taking a multiple integral over the values of xi for I between 1 and n minus 1. So for all these time steps, I between 1 and n minus 1, because 0 and n, they are fixed, the endpoints I already told you. For that we can take a multiple integral over the values of xi, because this is what is varying, xi is varying. Suppose for I equals to 1, x1 is varying. There are many possible values of x1, x1 prime, x2 prime. So we take into consideration everything. Then for x2 and so on. Like this we can construct, we can get the total sum over paths, or over all the paths. Say, and clearly n epsilon is tb minus ta, because tb minus ta means this net time interval tb minus ta, and that is just 0 to n, and each is spaced epsilon. So if I multiply epsilon n times, I will get this length, which is just tb minus ta, the net time interval between the final point and the initial point. And epsilon is just the difference between the gap between two successive time steps. So it's ti plus 1 minus ti, or you can also write ti minus 1, whatever, doesn't matter. And t0 is ta, tn is tb, and x0 is xa, xn is xb. Just a notation, right? Now since 0 and n are the initial and final points which are fixed, we do not integrate over them. The integration over 1 to n minus 1. So now the resulting equation is, we get this k b comma a, that is the propagator, or whatever you say, kernel from a to b, that is proportional to all of this integration. See this, I've just given dot dot dot, so many integrations of this thing. Phi is the contribution. Phi is just this thing. You see this thing, e I over h cut s. That's just this c. Okay, I told you this c, right? I told you. This c is basically phi, some constant times e over I, e to the I s over h bar. This constant is it takes a different form in this expression, which you will see. But this phi corresponds to that c here. Okay. So this phi and this phi is a function of s, x, and this is how we denote it, because it's a function of Lagrangian and everything, right? Of position, time, everything, action. Yeah. So and we did this, all this integration over dx1, dx2, and so on till dx n minus 1. Like I told you, we take from 1 to n minus 1. For 0 and n, they're the endpoints, they're fixed. Now to obtain the more accurate sum, we have to take the limit epsilon tends to 0. That means basically, see, if epsilon is a very a finite number, that means we are only considering specific points in time. But ideally, we should take all the values. So that means we cannot do that by hand. But that's why we assume the limit epsilon tends to 0. Or equivalently, we can say limit n tends to infinity, because n is the number of time steps. So if the number of time steps is very large, that means we have divided into very small intervals. That means epsilon tends to 0, or equivalently n tends to infinity. So yeah, we take the limit epsilon tends to 0 to make the time steps smaller. And we also define a normalizing factor, and here the form of the factor is a to the minus n. That means 1 by a whole to the power of n. That means 1 by a n times, where a is given by the under root of 2 pi I h bar epsilon over m. Or this thing raised to the power half. That means under root. M is the mass of that particle for which we are trying to find out this propagator. And epsilon is of course this time step, and h bar is the reduced Planck's constant, I is the imaginary number, and pi is you know what pi is. So now why is this form of the normalization constant, we will derive it in this video itself, just after a few pages. So that means by taking into consideration all this, finally we can write our kernel k b comma is equal to limit epsilon tends to 0, 1 over a, all this integration e to the I over h bar s b comma a, the action from a to b, dx1 over a, dx2 over a, and so on till dx n minus 1 over a. I mean, it's good to write in this form, but yeah, what we're essentially doing is that we had a raised to the power minus n, the net normalization factor, normalization constant. So that means 1 over a n times. So see, from 1 to n minus 1, we have this dx1 to dx n minus 1. So if I just multiply each of these with 1 over a, we have from 1 to n minus 1, we have all the a's used, all the 1 over a is used up here. So we have only 1 over a left, because a to the power minus n minus 1 times we've already used, so 1 more left, and that is here. You see, that is 1 over a at the outside the integral. And here we have not written it, but basically the limit of the above integration is from minus infinity to plus infinity, because we are considering see, the integration is over x, and ideally we are considering all the possible paths, so minus infinity to plus infinity. Yeah, in general the limit of the integrations we'll be dealing with in all the cases except this time integrations and all from ta to tb. Otherwise the limits are from minus infinity to plus infinity. This is for all the cases. Let me just tell you, I have not written it time and again to keep things tidy, but yeah, this is the assumption. I've just written it, and this is actually this integration. I've just only given this symbol, but actually this means that the limits are from minus infinity to plus infinity. And the general notation of the kernel is this: a to b integration e to the I over h bar s b a d capital dx. This is a general notation, because we are writing all of those dx1 over a, dx2 over a, and then also many integrations from minus infinity to plus infinity. We can write this in a general notation, general form like this, and this is what we call a path integral. Now let us discuss this multiplicative law of propagator, which is very important, and we'll be using this result also, so it's important, right? For events occurring in succession, see, right now we are in page 13. I have discussed two or three pages in between also. So let's say we have covered about 15 pages, and this video is 1 hour. So I mean, and we have 63 pages. It's gonna be almost a 4. I did that. Do you remember that modular symmetry video I recently dropped on my channel? For those of you who follow the channel, that was a 4 hour 30 minutes long video, and that was the longest video I recorded. In that video also, I explained the modular groups and all this mathematical stuff. So I think this video is probably gonna be as long as that, if not more. Anyway, Okay, so for events occurring in succession, basically see, suppose we choose some, see from A to B, we have many different paths in this x versus t we have plotted. Now we choose some intermediate point C. Say TC is some time between TA and TB, right? So the time coordinate of the point C is TC and the time coordinates of the points A and B are TA and TB respectively, and the corresponding space coordinates are XA, XC and XB. I mean the space values, whatever. So basically, we have just chosen a point C in between. Now we will basically the approach. The idea is that we want to find out the kernel B comma A. That means all the paths from A to B. So if we introduce a point C in between, initially we introduce a fixed point C. That means first we have reduced the problem to A to C. Now in this case, A is the initial point, C is the final point. Both of them are fixed. First we consider all the paths from A to C, and similarly then we consider all the paths from C to B. Here C is the initial fixed point and B is the final fixed point. And then we integrate both of these kernels, that is the kernel C comma A, kernel A to C, so kernel C comma A and then kernel B comma C. We multiply both of these kernels and then we integrate over dxc, because we integrate over all the possible values of C, because first we choose a particular C and then we consider all the paths from A to C and from C to B. But suppose if I chose a different value of C, then what? Then we could then there is a kind of then we have to consider all the paths A to that value of C, and then from that value of C to B all the paths. So basically that's why we integrate. In the end we integrate minus infinity to plus infinity with the variable of the integration being xc, to take into account all the possible values of C. So essentially in this way also we can actually find out the kernel B comma A. And it might seem like very complicating things by introducing C in between, but actually this thing is used a lot in calculations. Okay, it makes calculations easier actually. So propagator k b comma is the probability amplitude for the particle to go from A to B, and similarly k b comma c is the same from C to B, and k c comma is from A to C. So let Tc be the jth time point Tj, like I said Ti from from 1 to n minus 1. So at some intermediate point J, say we have this Tj which is our point C. So basically we're just replacing Tc with Tj and Xc with Xj. I mean you can just for a better understanding, nothing else. Now assuming there is no potential, that means a free particle, no potential, no forces acting on it, that means we can write down the action S as m over 2 x1 minus xa over epsilon whole square plus this. See where is this form coming from, right? Because action I told you was integral L dt. So let me show you, don't worry, I'm showing you. Anyway we will cover all of this. Okay, so yeah, you see action S is integration L dt, so it's for a free particle the potential energy is 0. So what is L? L is T minus V, kinetic energy minus potential energy. So if V is 0, then L is just T, the kinetic energy, which is m x dot square over 2 as I've written here. So integration L dt is integration m x dot square over 2 dt. Since epsilon is the discrete time step, we can replace dt with epsilon. Dt is the shortest the time interval, and we can replace that with epsilon. Epsilon is the discrete time step, and the integral with a summation. Because since we are taking discrete time steps, not continuous, we no need of the integration. I mean equivalently we can write this from this we can write that this is a summation I equals 1 to n m over 2 x dot square. Okay, see x dot square. What is x dot square? X dot means the time derivative of x, that means dx dt square, and again dt is epsilon, so dt square is epsilon square in the denominator, and the numerator, what is dx? Dx is the discrete gap in xi, that means xi minus 1 we can write dx, the gap in the position, the x coordinates, the two successive xi values, or we can also write xi plus 1 minus xi, but yeah, here we have used this form xi minus 1. So the x dot square is this thing, xi minus 1 whole square over epsilon square. So see m over 2 x dot square, in place of x dot square I have written this thing, into in place of dt I have written epsilon, and in place of the integration I have just written summation I equals to 1 to n, because we have divided the times into discrete steps from 1 to n, I mean into n discrete steps essentially. So here we have epsilon square in the denominator and just epsilon here, so 1 epsilon will cancel, and ultimately we are left with m over 2 epsilon summation I equals to I1 runs from 1 to n xi minus 1 whole square. So this is how we have kind of discretized our action. Okay, so we were discussing here. Now you uh, see here we have written what? M over 2 epsilon, see M over 2 and here is the epsilon, xi minus xa whole squared plus M over 2 epsilon xj minus 1 whole squared. This is in between, see, plus dot dot dot, I have written here dot dot dot, a lot of terms. Then I have shown this term in between, plus the next term will be M over 2 epsilon xj plus 1 minus xj whole square plus dot dot dot, the last term will be M over 2 epsilon xb minus xn minus 1 whole square. So basically we can take M over 2 epsilon common from all these terms, and we are left with x1 minus xa whole square plus dot 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 xj minus 1 whole square plus xj plus 1 minus xj whole square plus dot 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 xb minus xn minus 1 whole square. So if you just compare, you can see the general form. This is nothing but this form here. See, M over 2 epsilon common, we have this summation xi minus 1 whole square. See, I 1 to n. So for the first if we put I equals to 1, we have x1 minus x0. 1 minus 1 is 0, but x0 means the initial point, so that is just xa. So the first is x1 minus xa. You see, if you just compare, you see we have written that precisely, we have written that here. You see, no, just a second. Yeah, you see the first term x1 minus xa. Then the last term, I can show you, the last term is summation was from I equals to 1 to n. So the last term, you see, what will be the last term in that case? You see, n. So that means xn minus 1. So this is xn minus 1 and xn is the end point, so that is xb. So xb minus xn minus 1. You see, that is what we have here as well. If you see xb minus xn minus 1. And here we have taken the intermediate points. There are a lot of points, but we have taken these two points, especially these two terms, because we are interested in this j point, in this c point. We are considering an intermediate point c between a and b. And we have just grouped all of these terms. First group is from this term up to this term. We have in this second bracket, and this is the second group. Now the xi's are xa, x1, x2, xj minus 1, xj, xj plus 1, and so on till xn minus 1, and finally xn or xb. Now let us denote the first part of the above expression of s as s xj comma xa, because this is basically the action from a to j. You see, the first the expression within the first second bracket, we start with xa, and then dot 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 we move up to xj. See, xj minus 1. So that is xa comma xj, right? And for the second term, we start with xj here, and we move up to xb. So the second part can be written as the action xb comma xj, xj to xb, and this is xa to xj. So that means the total action s is this plus this. So it can be written as s xj xa plus s xb comma xj. And s we know is e to the I s over h bar. And now this is the s we can write. Now so what will be e to the I s over h bar? So since s is s this plus s this, so e to the I s over h bar will be e to the I over h bar, and in place of s we can just write s xj comma xa plus s xb comma xj. And yeah, of course, if we have e to the a plus b, we can write e to the a into e to the b. So that is what I have done here, e to the I over h bar s xj comma xa into e to the I over h bar s xb comma xj. Thus now we can write this kernel b comma a as limit n tends to infinity, or equivalently limit epsilon tends to 0, right? One, see, this expression we already had, right? This expression I am talking about, right? This one here, 1 over a, then limit epsilon tends to 0, 1 over a, and all this integration, then e to the I over h bar s b comma a, then dx1 over a, dx2 over a, and so on till dxn minus 1 over a. So just this expression only I have written there, but in place of this thing, in place of s b comma a, I will write s b comma c, s c comma a, or yeah, in our notation xj xa, whatever. So that is what we have written here. You see, limit n tends to infinity, 1 over a, all this integration, e to the I over h bar s b, yeah, this thing we have written here. See, we have just kind of regrouped or rearranged the term, but it's the same thing. So limit n tends to infinity, 1 over a, then first integral dxn minus 1 over a, and so on till integration dxj plus 1 over a, dxj over a, dxj minus 1 over a, and then dot 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 integration dx2 over a and dx1 over a, and then finally in place of e to the I over h bar s, I've just broken it into this. Basically, why we are doing this, see, all this integration and all these things in between, the j terms are also there, but here since we're interested in j, I have explicitly written these three terms. Now rearranging once more, if you see, 1 over a into, I mean up to this dx j plus 1 over a, and then this for this term e to the I over h bar s x b comma x j, I mean from j to b. That is what we this part we are putting in this, the first part, in this bracket, right? Basically this means the action is from j to b, and that is what we are doing the integration also from j plus 1. That means j to b action means j and b are the fixed points. So integration will be from the point right after j, that is j plus 1, to the point right before p, that is n minus 1. See, dx j plus 1 to a integration, then dot 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 so on till we have dx n minus 1 over a integration, and we have this 1 over a here, no issues. Now let us keep this thing dxj integration separately, and with this also there should be a 1 over a. 1 over a is with each of the term. That 1 over a let me bring here. See, this is the 1 over a we previously wrote with integration dxj. So this we bring in the second bracket, I mean in the second expression, which is also enclosed in brackets. And here we write from dx j minus 1 over a and so on till dx 2 over a, dx 1 over a, and this thing e to the I over h bar s xj comma x. That is the action from a to j, and since a to j, a and j are the fixed endpoints, here we take the integration from x1, that means the point right after a is x1, xa is x1, and the point right before xj is xj minus 1. So you see here the integration is dx1 over a and so on till dxj minus 1 over a. So now in this first expression you see 1 over a. See, what was the definition of kernel, the original definition? How did you define the kernel? See, you look at this definition. K b comma a is limit n tends to infinity or epsilon tends to 0. 1 over a, 1 over a should be outside the integration, and then all these integrals, and then the action is b comma a and all these things. Here the action is a to b, and integration is over c. Right after a we have x1, and right before b we have xn minus 1. So, but this is the general definition of a kernel, right? So here in this term you see we have limit tends to infinity 1 over a, and then all these integrations, and the dx j plus 1 to x dx n minus 1 over a's, and the action is also from j to b, right? So this first term in this bracket, that can be written as k xb comma xj or kb comma j. From j to b we can write this, right? Then integral dxj, let us just keep it as it is, and this second term in the same way we can also write this as this second expression. We can write this as kj comma a, kernel from a to j, or kxj comma xa. So that is what we have written here, you see. Thus kb comma a. So ultimately see this expression kb comma a becomes limit tends to infinity, this thing k xb comma xj multiplied by k xj comma xj, and the total integration with respect to dxj, with respect to xj. So kb comma a we get integral dxj k xb comma xj k xj comma x, just what I told you. And since j is equivalent to c, and in alternate notation, I mean instead of writing xb, let's just write b, and xj c and xa a. So in alternate notation, in a more beautiful compact notation, we can write this kb comma a is equal to integral dxc kb comma c into kc comma dxc, see xj is xc basically, because j corresponds to c. So this is the multiplicative law of propagators. We are just multiplying these two propagators or kernels, whatever. So basically first we fix the intermediate point c and sum over all paths from a to c, that is the kernel c comma a, and then sum over all paths from c to b, that is the kernel b comma c. I mean this should be I've just somewhere I've written capital B and here I've written small b, so please ignore that. I mean please don't get confused with that. Now so we split the sum over all paths from a to b into the sum over all paths from a to c and the sum over all paths from c to b. Okay, this should be from a to c at this point. From a to c. I've somehow forgot it, somehow missed it. Yeah, so basically we have split the sum of overall paths from a to b into two parts, a to c and then c to b, right? And finally we integrate from minus infinity to plus infinity with respect to xc, because this is just to consider all possible intermediate points c. Tc is fixed, we have fixed the time, but for the fixed tc there could be many possible values of xc, so we are integrating with respect to xc, integration dxc. So that now we have a complete equivalent description of the original sum over paths from A to B, that is the kernel B comma I. So we can write that kb, this thing we can write kb comma is equal to integration dxc kb comma c into kc comma I. And we can actually generalize this from any number of intermediate variables also. It's not like we can take we need to take a single point C in between A and B. We can take 2 points, suppose C and D, suppose A and B, then we take a point C in between and also a point D in between. We can take 3 points, 4 points, 5 points, no, we can generalize this up to n points indefinitely. So if we can generalize for any number of intermediate variables. For instance, if we take a point D in between, then we can also write kb comma equals to integral dxc integral dxd kb comma d kd comma c kc comma I. The derivation is the similar one. I have not shown it, but it's the same thing, just an extension. I mean, it's kind of like an induction, mathematical induction. Now, yeah, since we have written in this form, here we have assumed that the point D is after point C. That means time TD is greater than TC. And of course, TB is the end point and T is the initial point. So, TB greater than TD greater than TC greater than TA. So, in that case, it will be the product of three kernels KB comma D, KD comma C, KC comma. KC comma means from A to C, then KD comma C means from C to D, and finally KB comma D means from D to B. So, you have broken the path A to B into two parts. Into three parts, A to C, C to D, D to B, by introducing two intermediate points C and D, right. Just a second. Yeah, now we are currently, just a second, yeah, okay. So we are in page 18 and its video is 1 hour 20 minutes. Fine, I'll manage it. I mean, I have no problem, but I know this video is becoming very long. I mean, it happens with most of my this kind of videos. But see, if you really want to understand path integrals very rigorously, you need time. It cannot be done in 1 hour, even in 2 hours, I guess. Yeah, if you're interested in the topic, I guess you will watch it, even if it starts long. And otherwise, I mean, anyway. So previously we have derived that kb comma a is limit epsilon tends to 0 1 over a raised to the power n, all these integrations, and then dx1 dx2 up to dxn minus 1 and e to the I over h bar s b comma. See, here we have I have written 1 over a raised to the power of n. I can break it into 1 over a 1 over a 1 over a n times, and I can keep a single 1 over a here and divide all of these variables by a to correspond to the other n minus 1 times 1 over a. That means dx over the form which we have been using previously, dx 1 over a, dx 2 over a, and so on. So this is the kernel A to B, whereas B is the action, and all of this I have already told, and normalizing factor also I told you, it's 2 pi I h bar epsilon over m raised to the power of half. And for a free particle, V equals to 0, so no potential field, so L equals T minus V, which is equals to just the kinetic energy in this case T, which is mx dot square over 2. So now what we want to do now, our aim right now will be to derive the mathematical expression for the kernel. This is but we have to solve the integration and derive the expression for the kernel. This is okay, fine. This is the general expression of a kernel. But we want to find the kernel for a free particle. For a free particle means we have to find the action, and in the action for the Lagrangian we will just substitute mx dot square over 2. Because free particle means it is no force is acting on it. It is not in any potential field. So this potential term V will be 0. And the notation of a free particle kernel is usually k naught or k0 b comma to denote free particle. So this is after we this is the form which we should get after we substitute the action for the Lagrangian and everything. This is what we should get. But the derivation is a bit long and bit lengthy, and it's a bit concept heavy. So that is what I will show you right now, the derivation. But before this, let me just here's a quick glimpse of the result which we hope to derive, that is k naught b comma. This is the kernel for a free particle. Keep in mind, k naught b comma is limit epsilon tends to 0 m over 2 pi I h bar epsilon to the power n over 2. Because see, this is 1 over a to the power n, and I told you which should be of the form. I will derive this also, but right now just I told you a should be of the form 2 pi I h bar epsilon over m to the power half. So 1 by a will be m over 2 pi I epsilon to the power half, and 1 by a raised to the power n will be this thing, m over 2 pi I h bar epsilon to the power n by 2. And then we have all these integrations and dx1 dx2 till dxn minus 1. and e to the I over h bar s. In there we have written e to the I over h bar, then m over 2 epsilons, then summation I equals to 1 to n xi minus 1 square. This just now I showed you, this is the expression for the action s. This is e to the power I over h bar s. So you see there is a I here, there is a h bar here, and other than that the expression m over 2 epsilon summation this thing, this is just the action s. I just now showed you m over 2 epsilon this summation. Since s equals integral L dt, and for a free particle only the kinetic energy term, and x dot is dx dt whole square, so dt is epsilon, so this thing, and dx is xi minus 1 whole square over epsilon square. So substituting all of this and using dt, putting dt equals to epsilon, and changing the summation integration to summation, since we are till now we are dealing with discrete time steps. Yeah, in the end we have this limit epsilon tends to 0, so it should take care of that, right? So then we are getting this. I mean, this is not the final result which we will get. Final result is coming. This is not the final result anyway, but yeah, this is just the next result which we just showed you. And where is this coming from? This thing in between the exponential function, that is I just showed you from this expression of the action for a free particle. So the equation for k naught b comma is a set of Gaussian integrals. The Gaussian integral concept is very useful in path integrals, in solving path integrals. Gaussian integrals are basically integrals of the form integration minus Gaussian integrals means limit is always minus infinity to plus infinity, okay, and the form of the integration is this kind of thing, okay, integration e to the minus a x squared dx. So here x is the integration variable, e is the exponential function, and a is just a constant. Or maybe a more general form, integration e to the minus ax squared plus bx dx, where a and b are constants. So since integrals of a Gaussian is again a Gaussian, we can carry out the integrations on one variable after the other, and at last we can take the limit epsilon tends to 0. But before we proceed, we need to know some general results about Gaussian integrals, right? So that is what we will do next. See, this is the most fundamental result of Gaussian integral which you can actually derive. It's not, the derivation is not very difficult also. Just a little bit of substitution. I have not shown that here. This is standard, very basic level derivation. So maybe BSc, I mean undergraduate level derivation, undergraduate first year level derivation actually. So yeah, this is that integration minus infinity to infinity e to the minus x squared dx is under root pi. Then integration minus infinity to infinity e to the minus a x squared plus bx dx, where a and b are constants, is under root pi over a e to the b square over 4a. Then this thing, if we have integration minus infinity to infinity e to the minus ax square plus bx plus c, where a, b, c all are constant, dx, this is equal to see, this we can write e to the minus x square plus bx plus c, we can write e to the c dx. Why? Because see, e to the a plus b is equals to e to the a into e to the b. So this plus we have broken, we have just split it into a different part. Why this plus? Why not this? Because see, in the first two terms there is x, which is a variable, ax squared and bx, but c is the constant. So this e to the c is also a constant. That means we can just bring this out of this integration. Now this thing, integration e to the minus x squared plus bx plus c dx, can be written as e to the c outside the integration, and integration e to the minus x squared plus bx dx. And this integration we already know that it is under root pi over a e to the b square minus 4a. So this can be written as e to the c under root pi over a e to the b square minus v square over 4a. Or now if we can also write it like this, because since e to the a e to the b is equal to e to the a plus b, we can write under root pi over a e to the b square over 4a plus c. This c we can just bring it here. So these are the standard results. This is all which we will need, nothing more. So now let us evaluate. Don't ask me why we are evaluating this particular function all of a sudden. You will understand why. This is because it will help a lot in our calculations. We are not just doing it out of fun, of course. So let us evaluate this integration minus infinity to plus infinity e to the minus k1 x minus a squared minus k2 x minus b squared dx. K1, k2 are constants obviously. So now see, minus k1 x minus a squared minus k2 x minus b squared, this argument of the exponential function. This, if we just kind of break it, just distribute it and everything, we will get minus k1 x squared minus k1 a squared, I mean just a second. Yeah, so x minus a whole square is x square plus a square minus 2xa, and then you are just multiplying minus k1 with each of these terms. So minus k1 x square minus k1 a square plus 2k1 xa. Similarly for this, minus k2 x square minus k2 b square plus 2 k2 xb. Now if we just bring all the x square terms together, the coefficient will be minus k1 plus k2 in bracket, you see, x into x square, plus 2 in bracket k1a plus k2b, this and this, x minus k1a square plus k2b square, k1a square plus k2b square, minus come. So now we can write it like this, see, minus ax square plus bx plus c. We can write it in this form, where capital A is a constant, k1 plus k2, we can see from this equation, and capital B is also constant, it is 2 k1a plus k2b in bracket, and capital C is also constant, it is minus k1a square minus k2b square, or if you write in bracket, minus k1a square plus k2b square, whatever. Now it's in this form. So now this integration, minus infinity to infinity e to the this thing dx, can be written as e to the minus ax square plus bx plus c form, and we already evaluated just now that this integration is the answer is just under root pi over a e to the b square over 4a plus c, and here we know what is a, what is b, what is c for our special this expression. So we get under root pi over a, that is under root pi over k1 plus k2, e to the b square by 4a, that is e to the b is 2 k1a plus k2b, so b squared is 4 k1a plus k2b whole square over 4a, so 4 k1 plus k2 plus c is this thing, and that is what I have written there, plus c. Now we can simplify this, k1a plus k2b whole squared, we can just break this down, break it, and if we just take the LCM k1 plus k2, we multiply k1 plus k2 with this also, then what we are left with, see, k1a plus k2b whole square is what, k1 squared a squared plus k2 squared b squared plus 2 k1 k2 ab minus, see, we are just multiplying k1 plus k2 with this thing, minus k1 a square minus k2 b square, so we have minus k1 squared a square, then minus k2 squared b squared, these two terms will be there, and then we have these terms also, minus k1 k2 a square minus k1 k2 b square. So clearly these minus k1 square a square will cancel out, plus k1 square a square, and k2 square b square and minus k2 square b square will also cancel each other. So we are left with ultimately, see, take the minus common, take the minus entirely out of the bracket, and we are left with k1 k2 a square plus k1 k2 b square plus 2 k1 k2 ab. So again, if I take minus k1 k2 out of the bracket, we are left with a square plus b square minus 2ab, because we have taken the minus common. So that is a minus b whole square. So that is what I have written here. You see, minus k1 k2 a minus b whole square, and in the denominator we have k1 plus k2. So this is the result. So we started with this thing. So integration minus infinity to plus infinity e to the minus k1 x minus a square minus k2 x minus b whole square dx is equal to under root pi over k1 plus k2 exponential minus k1 k2 over k1 plus k2 a minus b whole square. This is what we get. So we will use this result. Just remember this, right? We'll use this result right now, right? So Lagrangian for a free particle is this m over 2x dot square or dx by dt whole square. Now you see here I've drawn this diagram. That's the same similar kind of diagram. This, but here the time is in plotted horizontally and xt vertically. Whatever, doesn't matter. So I've just traced one path for you. All the time steps are epsilon, spaced epsilon, t1, t2, tn up to tn, t0 to tn. T0 is ta and tn is tb, and here x0, x2, x1 and so on. See here x0 to x1, so x1 and then it comes down to x2. It's not necessary. In case of time, it's always true that t0 is less than t1, t1 is less than t2. It's kind of linearly increasing and with equal intervals. But that need not be true for this x size, because you see, x0 to x1, x1 is at this point, but then we come down, so x2 is actually lesser than x1. That's possible, but x2 is at a later time, t2 is greater than t1. So anyway, so between t0 and t1, dx is x1 minus x0. Between just t0 and t1, just in this point, this is x1 minus x0, the dx. So dx dt is x1 minus x0 over epsilon. Dt is always epsilon, I told you. Between t1 and t2, dx is x2 minus x1, so dx dt will be x2 minus x1 over epsilon, and so on. Now the action can be written like this, that integration ta, this is the definition of action, right? Integral ta to tb, integration from ta to tb, and since for a free particle, m over 2 x dot square, that is dx dt whole square dt. And since discrete states, we do not, in the same way, we do not need the integral, and we can replace this dt with epsilon, So and we can just replace the integration with the summation, and see like this, for between t0 and t1 we have x1 minus x0 over epsilon dx dt. Then for t1 to t2 we will have x2 minus x1 epsilon. So here I've shown you a simple example, you see. Yeah, so in general we will have m by 2 common, and we will have x1 minus x0 over epsilon whole square, because this is dx by dt, say x1 minus x0 over epsilon, so dx by dt squared will be this thing, plus x2 minus for the next set, for the next interval, x2 minus x1 over epsilon whole square, and plus dot 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 so on until finally xn minus 1 over epsilon whole square, and into epsilon, because this dt is there, right, this dt, this dt, so into epsilon. Now first of all we'll start with a very simple case, simplest case, that we from ta tb we will divide it into just two equal parts, each of length epsilon, time interval epsilon, in ta tb. So that means just ta to t1 and t1 to tb, not like t1 t2 t3 and up to tn minus 1 and then tb, not that. We will arrive there, but let us start with the simplest case, just one single time step in between the initial time ta and the final time tb, ta t1 tb. So let ta be equal to t0, t1 is t1 and tb be t2, and the correspondingly the x of ta is xa, I mean at ta the corresponding x is xa, and similarly xb, and this is x1. So then you see I will only have two terms in my action, s, it is just m over 2 x1 minus xa over epsilon squared plus xb minus x1 over epsilon squared, and into epsilon. Why? Because see, just two terms. So for ta to t1 it will be what, x1 minus xa, x1 minus xa over epsilon whole square, this is dx dt for this ta to t1, and for t1 to tb it is xb minus x1, and then that is all we have, ta to t1 this first, and then t1 to tb second, so two terms only. And since in both these terms epsilon squared, so we can just cancel this epsilon, and ultimately we have m over 2 epsilon x1 minus xa squared plus xb minus x1 squared, and this is s, and s is a function of x1 only. See, this in this expression xa and xp are the initial endpoints which are constants, and mass is a constant also, epsilon is also the fixed time interval, it's also a constant. So this s is only a function of x1. See, here we have x1, here also we have x1. x1 is the only variable here, right? Because yeah, we can change x1 for a particular x1. We like in the same thing we did when we were discussing the multiplicative law of propagators. We choose a c, but we can change c. That is why we integrate this product of both the kernels with dxc, integration dxc. Similarly here x1 we can vary, and that is why we will integrate over dx1. See, I showed you this picture, right? Yeah, this picture. No, not this picture. So when we are saying that this is varying, I mean in the sense that xi means, see, a lot of x's are possible at a particular level. See, at one x1 prime, x1 double prime, a similar concept I just showed you, so that I just explained the picture a few minutes back. So it should be, if you have understood it properly at that point of time, it should, I just flash the picture so that you can just so that you can recall it, right? So now let us evaluate this e to the minus ks dx1. K is some constant. Now you may ask that why are we evaluating k? Basically, see, we have the form of this e to the I over h bar s. That is the form of the propagator. I know that. But yeah, for ease of calculation, first we start with e to the minus ks. Yeah, later we will substitute minus k with I over h bar, and then we will have e to the I over h bar s. So integral minus infinity to infinity e to the minus ks dx1 will be then what? E to the minus k m over 2 epsilon, and this thing x1 minus xa whole square plus xp minus x1 whole square in and this is multiplied with both the terms km over 2 epsilon dx1, because nothing, we have just in place of s we have just substituted this thing here, m over 2 epsilon, these two terms, nothing else. Now you look at the form of this integration. We just now we evaluated, this is where I told you we'll be using the result which we derived in that Gaussian integral result. See, we evaluated this integral e to the minus k1 x minus a square minus k2 x minus b square. See, we have x minus a square, I mean here it's x1 minus xa square, but the same form, and xb minus x1 square. So x1 is the only variable, x and xb are constant. Here also you see x is the variable, a and b are constants. And since x minus b square is the same as b minus x square because it's squared, and here you see it's xb minus x1 squared, so kind of b minus x squared, doesn't matter. So this integral we evaluated just now. Yeah, this thing, right? This thing we just evaluated and we got this expression, which I've also written here for your reference, that under root pi over k1 plus k2 exponential minus k1 k2 over k1 plus k2 a minus b squared. So here k1 equals to k2 equals to km by 2 epsilon. See, between both these terms we have the same thing, minus km by 2 epsilon, this, then minus km by 2 epsilon. So here k1 and k2 are equal, and it's equal to km by 2 epsilon. So in our case, this e to the minus ks dx1 will be under root pi k1 plus k2 will be means 2 k1, because k1 is equal to k2, that means 2 km by 2 epsilon, that is just km by epsilon, 2 cancel. So yeah, pi over km by epsilon, that means pi epsilon over km under root. That is what we have if we just multiply, substitute the value of k1 and k2 here. Exponential, here also I have just put in place of k1 as well as in place of k2, I have just put this expression km over 2 epsilon, and then I get what, k1 into k2, that means k square m square over 4 epsilon square, into I have 1 over k1 plus k2, that means 1 over km by epsilon, 2 km by 2 epsilon, so km by epsilon. So that means epsilon over km. Now there will be some cancellations, and ultimately I am left with, yeah, this. And here we have a minus b whole squared will be, here we have xa minus xb whole squared, that is in our notation, otherwise same thing. So note that yeah, I told you x minus b squared is equivalent to b minus x squared also. So this integration e to the minus ks dx1 is under root pi epsilon over km e to the minus km by 4 epsilon. See, here we are left with km by 4 epsilon, rest everything cancels out, xa minus xb whole squared. Right. Now we will show you, I told you previously that like why this normalization constant, it should be of the form, this form, I myself forget the form, but yeah, you don't have to remember it, just you need to understand it, right? So this form, I told you that this is the how the normalization constant looks like. Yeah, the normalizing factor a is 2 pi I h bar epsilon over m raised to the half. So where is this coming from? We'll see, right? See, the Gaussian function e to the minus x minus a squared over 2 sigma squared. This is we learn in a normal distribution and everything. This is the general Gaussian function, right? So this is normalized to normalize this function e to the minus x minus a whole squared over 2 sigma squared. We need to multiply this by 1 over sigma into under root 2 pi, because we know that this integration minus infinity 1 over sigma under root 2 pi, and then this function e to the minus this thing dx equals to 1. Now to normalize e to the minus km over 2 epsilon x1 minus xa whole square, that is what we got here, this thing. See, here we got e to the minus km over 4 epsilon, but here we are trying to normalize e to the minus km over 2 epsilon. Why? We will see later. I mean, just now we will see, but here actually we let us first consider this form, because that will be easier in our calculations, right? I mean, here I'm not just it's not a continuation of this calculation. I'm just telling you that okay, let us try to normalize this function. Why I'm assuming this particular form will soon become clear to you, become apparent to you. Now to normalize this, we need a normalization constant 2. Now on comparison, you see here we have e to the minus x minus a squared over 2 sigma squared. And here we have e to the minus km over 2 epsilon x1 minus x squared. So in comparison, you see 1 over 2 sigma square is equal to km over 2 epsilon. So that means sigma is equal to under root epsilon over km, right? Because x1 minus x square, and here we have x minus a square. So those are the same thing. So and minus negative sign is also there. So that means 1 over 2 sigma square must be this, whatever is remaining, km over 2 epsilon. So from there we get sigma equals to this under root epsilon over km. So 1 by sigma into root 2 pi, because we have compared with this form. So and to normalize this form, we multiply by 1 over sigma into root 2 pi. So here also we will multiply with 1 over sigma into root 2 pi, but in place of sigma we will use this expression, because that is what we derived for our form. So we have under root km over 2 pi epsilon. So this is our 1 by a normalization constant, under root km over 2 pi epsilon. Now we have not yet substituted the value of k, which we will do later. Once we do that, you will see that the form is under root m over 2 pi I h cut epsilon, which is the form which I showed you, which we assumed from at the beginning. Now we had s equals to e to the minus km by 2 epsilon x1 minus x squared minus km over 2 epsilon xp minus x1 squared. This was s, right? Because you see, where I wrote, yeah, see, this is s. S is m over 2 x1 minus x squared over epsilon plus xb minus x1 squared. I mean, just a sec, just give me 1 second. Yeah. No, just a second. We are saying s equals e to the minus. Just a second. This is I think I'm talking about. Okay. Km over 2 epsilon x1 minus x squared by and then xp minus x1. Sorry. Yeah, so that means yeah, this is not s. We had this is e to the minus ks. Okay, I'm sorry about this. This is kind of, I don't know if I can annotate here, but or kind of draw or anything. Let me see. Let me choose this black. Okay. So this is not s. This is e to the minus ks. I hope I mean, I hope it's at least understandable, right? So this is e to the minus k is equal to e to the minus k, and in place of s, I have just substituted m over 2 epsilon x1 minus x squared plus m over 2 epsilon xp minus x1 squared minus k if we take common. And this is the form of s which we already know, right? This form of s, m over 2 epsilon x1 minus x squared plus xp minus x1 squared. That is what we have written there. So this is e to the minus case. We already had this. Now, so for this equation, then see, to normalize this thing, e to the minus km over 2 epsilon x1 minus x squared, our normalization constant is 1 over a, that is under root km over 2 pi epsilon. Now in this e to the minus case, we have actually two terms, e to the minus km to epsilon x1 minus x squared into e to the, if we just express it like that, into e to the minus km by 2 epsilon xp minus x1 squared. So to normalize this first exponential, we need 1 over a, and to normalize the second exponential, we also need another 1 over a. So we have 1 over a whole squared, and that is just 1 over a was what? Under root km over 2 pi epsilon. So 1 over a whole square will be just km over 2 pi epsilon. So the normalized solution is km over 2 pi epsilon into this thing which we already got. This thing means, yeah, this thing, under root pi epsilon over km e to the, this thing we already saw using the Gaussian identities and formula. We just solved this integration e to the minus kx dx1, and this result we got just for the integration. So that is what is written here, and into this thing km over 2 pi epsilon, this is the normalization factor. And why is this normalization factor? We just derived it here. We just kind of showed you here. And yeah, now we can write it as under root km over 2 pi 2 epsilon. What I have, okay. So this is 1 root km in the denominator and just km in the numerator. So ultimately we will have a under root km in the numerator, and pi e will cancel, and we will have a under root pi e, under root 2 pi e in the denominator. Under root 2 pi, so pi cancel, yeah, pi will be there, so 2 pi e. So this 2 is not under the root, so to put this, to bring this 2 inside the root, we have under root 4 pi e. So we can write this as 2 pi into 2e. I mean epsilon. I'm saying e. It's actually epsilon. So basically we see just these two terms. If we evaluate, we will get this. Okay, under root km over 4 pi epsilon. But in place of 4, I have written it 2 pi into 2 epsilon. And inside this, I have not changed anything except that km over 4 epsilon. I have just written km over 2 into 2 epsilon. Why am I doing this? I'll show you. Because you see, in this case, the simplest case, we divided our path into two parts, T8, T1 and then T1, TP. So there are just two epsilons. So that means what? That means 2 epsilon will give me this entire TB minus TF, because from the initial point T8 to the final point TP, there are only two discrete time steps. So 2 epsilon. So the time, net time TB minus TA is just 2 multiplied by epsilon. basically, of course, epsilon is TB minus TA by 2 in this case, because here epsilon in general is TB minus TA by n, if we divide in n number of parts. Here we have divided into 2 number of parts, so TB minus TA by 2, where TB and TA are the endpoints. So 2 epsilon is TB minus TA. Now that means in this expression we can also write, in place of 2 epsilon, we can write TB minus TA. So we can write under root km over 2 pi TB minus TA exponential minus km over 2 TB minus TA xa minus xb whole square. That's why we have written it in, we have just kept 2 epsilon separate. Otherwise you could have written 4 pi epsilon and here 4 epsilon. That is not wrong mathematically. Now so this is for if we just have 2 epsilon. Now for the time interval TB minus TA divided into 3 equal parts. Now if we divide into 3 equal parts, in that case TB minus TA over 3 will be epsilon, or 3 epsilon will be TB minus TA. So in this case, what see, in this case the action will be, first of all, m over 2 x1 minus xa over epsilon whole square, that is the dx dt whole square for a to 1, because dt is epsilon and a to 1 means x1 minus xa. Then x2 minus x1 over epsilon whole square, that is the dx dt whole square for 1 to 2, and finally xb minus x2 over epsilon whole square, that is from 2 to b. So that is a to b, that means, and there are 2 points in between, we are dividing into 2, so that means we are dividing into 3 equal parts, 2 points, 1 and 2 in between, so that means a to 1, 1 to 2 and 2 to b, 3 parts. And yeah, this dt will be this epsilon. So again we can cancel this one epsilon with the epsilon square in the denominator, and we get the action to be m over 2 epsilon x1 minus xa squared plus x2 minus x1 squared plus xb minus x2 squared. 3 terms in this case, obviously. In the previous case we had only 2 terms. Now here the normalization constant will be 1 over a cube, because here e to the minus ks will be, see here, this is our s action. So e to the minus ks, if we want to evaluate for this case also, it will be e to the minus k m over 2 epsilon, then these 3 terms here, 3 terms. So that means we can just break it and like write that e to the minus k m over 2 epsilon x1 minus x squared into, or multiplied by, e to the minus k m by over 2 epsilon x2 minus x1 squared into e to the minus k m over 2 epsilon xb minus x2 squared. So that is this is basically a product of 3 Gaussians, and here we have 2 variables x1 and x2, xa xb are fixed. Now anyway, since with it's kind of 3 exponential 2, and of this form minus km over 2 epsilon x1 minus x, the same form. So to normalize one exponential you need 1 over a, so to normalize the 3 exponentials you need 1 over a cube. But yeah, but here 1 over a, this general form km over 2 by epsilon, this still holds. And now the integration, let us say I, it becomes 1 over a cube, then 2 integrations e to the minus k's dx1 dx2, because here we have 2 variables x1 and x2. So we integrate with respect to dx1 and we also integrate with respect to dx2. In the previous case, if you remember, we just evaluated e to the minus kx dx1 only, because dx1 was the only variable. Here it is integral, double integral e to the minus kx dx1 dx2, and the normalization constant is 1 over a cube, obviously. So I've just in place of s, I've just substituted this total expression for s. Now first we integrate with respect to x2, treating x1 as constant, and then we will integrate with, finally we will integrate with respect to x1. So that means 1 over a cube integration dx1. Okay, so here we have treating dx1 as a constant, and now this let us write this e to the minus km over 2 epsilon x1 minus xa squared, because this term there is only x1 and xa is anyway a constant, and x1 is also treated to be a constant in this part, because right now we are evaluating the x2 part. So we are just bringing this separate, we are just separating this integration dx1 and this term, exponential term. This is the constant part, see I have written it here, x1 part constant. And now we are left with integration dx2 e to the minus km by 2 epsilon x2 minus x1 squared plus xb minus x2 squared. See here in both the terms there is x2, so we cannot treat it as a constant. So this we will evaluate first. This is the constant as it is, and now this thing. Now if you remember, if you compare, in the previously we had we derived we derived that where am I? Where was I? Give me 1 second. Okay, yeah, so we derived that previously that okay, yeah, So integration e to the minus km over 2 epsilon x1 minus x squared plus xb minus x1 squared dx1. This integration is equal to under root pi epsilon over km e to the minus km over 4 pi xa minus xp squared. Now here we have a similar expression. You see, if you see just this part, not the constant part, just this x2 part, we have dx2, integration dx2 e to the minus km over 2 epsilon x2 minus x1 squared plus xb minus x2 squared. There we had integration dx1 e to the minus km over 2 epsilon x1 minus x squared plus xb minus x1 squared, right? Let me still check once. Yeah, this is what we had, x1 minus x squared xp minus x1 squared. But here we are having here the integration is with respect to x2, and here we are having, you see, the same thing here, everything else is same, except here we are having x2 minus x1 squared plus xb minus x2 squared. Anyway, it's a square term, so whether you write x2 minus x1 square whole squared or x1 minus x2 whole squared doesn't matter. And here x1 is being treated as a constant, so that means here this in this part the integration is with respect to only x2, so x1 is a constant, so it is of the same form. Now this part we can write under root pi epsilon over km e to the minus km over 4 epsilon x1 minus xp squared. Here the initial and final the endpoints are x1 and xp. There we got the value to be the integration solution to be the same form. See, under root pi epsilon over km e to the minus km over 4 pi xa minus xp squared. There xa and xp. Here also we get the same thing, e to the minus km over 4 pi, but here x1 minus xp whole squared. So we have evaluated this part also. Now you see, if we look at this total expression, we have no x2 term. Now it's entirely an equation in terms of x1. See, here we have x1 and here also we have x1. So now we can write this as 1 over a whole cube integration dx1 e to the minus km over 2 epsilon x1 minus x squared. Then again this thing under root pi epsilon over km e to the minus km. This instead of 4 epsilon I can write e to the minus km 2 into 2 epsilon xb minus x1 squared. See, x1 minus xb whole squared is the same as xb minus x1 whole squared. Now let me just bring this constant under root pi epsilon over km outside. So 1 over a cube under root pi epsilon over km, we have integration this term e to the minus km over 2 epsilon x1 minus x squared. Then we have this term e to the minus km over 2 into 2 epsilon xb minus x1 squared, and then we have dx1. So that means we have, yeah, this thing we have. Now what we can do is that yeah, we had this thing, right? Perfect. Yeah, so both these exponential terms we can just write, see, this is of the form e to the a into e to the b, so we can write e to the a plus b. That is what we have done here. Now see, this is this form exponential, this entire argument of the exponential function minus km by 2 epsilon x1 minus xa whole squared minus km by 2 into 2 epsilon xb minus x1 whole squared. Now we already evaluated this thing, right? Integration e to the minus k1 x minus a squared minus k2 x minus b squared dx, and we got this. Here also similar form, but here you see k1 and k2 are not equal, like in the previous in one example we did they're equal, but here they're not equal. Here k1 is km over 2 epsilon and k2 is km over 2 into 2 epsilon. You see, this is k2. So accordingly, if we calculate this side, a pi over k1 plus k2 under root, then exponential minus k1 k2 over k1 plus k2 a minus b squared, and here a minus b, a corresponds to xa and b corresponds to xp, and x corresponds to x1. See, here k1 is km over 2 epsilon, k2 is km over 2 into 2 epsilon, and k1 k2 will be k squared m squared over 8 epsilon squared, and k1 plus k2 will be yeah, k1 plus k2 will be what? Km over 2 epsilon common, if I take, we have 1 plus half, that means 3 by 2. So 3 by 2 into km over 2 epsilon, that means 3 km over 4 epsilon, that is k1 plus k2. So we get 1 over a cube, this thing under root pi epsilon by km, this is already there, and this entire integration, in place of this we can write it this that under root 4 pi epsilon over 3 km, because this is pi over k1 plus k2, that means 3 km in denominator and 4 epsilon and pi, so 4 pi epsilon, this thing, and then exponential minus k1 k2 over k1 plus k2. So k1 k2 is this thing, k square m square over 8 epsilon square into this thing k1 plus k2. Actually it's 1 over k1 plus k2, so it's 4 epsilon over 3 km, just a reciprocal, and into we have xa minus xb whole square. So here a few things will cancel out, and ultimately we are left with what? 1 over a whole cube under root 4 by 3. From here we are getting under root 4 by 3. And see, this is pi epsilon over km under root and again pi epsilon over km under root. So together they will just, we are left with just simply pi epsilon over km. And then exponential minus km over 2 after we cancel out these km's, and then 4, 8, we are left with 2, and yeah. So minus km over 2 epsilon, and here we have a 3. So minus km over 6 epsilon xa minus xp whole square. Right? I know I might be moving a bit fast, but yeah, this is just all the steps are clearly written down, so you can just pause the video and watch it in slow motion, I guess, because here is no new fundamentally new concept to understand, just mathematics. Not very easy mathematics, I admit, but yeah, just mathematics. Yeah, now we can say that this is what pi epsilon over km. Okay, so now we have that this 1 over a was under root km over 2 pi epsilon, right? So that means here we have 1 over a cube, right? So 1 over a cube will be just a second. 1 over a was what? I'm sorry. Yeah, 1 over a was km over 2 pi epsilon to the power half. So 1 over 2 to the power 3 will be km over 2 pi epsilon to the power 3 by 2. So km over 2 pi epsilon to the power 3 by 2. But yeah, that means to the power half plus 1, that means to the power half, and km over 2 pi epsilon. So km over 2 pi epsilon we had, right? Km over 2 pi epsilon, yeah. So to the power 3 by 2 means just km over 2 pi epsilon, we have that this thing here, into km over 2 pi epsilon to the power half, that is under root km over 2 pi epsilon. But we also have under root 4 by 3. So 4 by 3 into 1 by 2, that is 2 by 3, because 1 2 will cancel with the 4, that means 2 by 3 and km over pi epsilon under root. So this 4 by 3 we have incorporated, and this 1 by a whole cube. So this entire thing is this thing, and this pi epsilon over km we have here pi epsilon over km. Now this thing will cancel km and pi epsilon pi epsilon. So ultimately we are left with this one more 2 is here. So if we want to bring this 2 inside the square root term, we need to make it a 4, and ultimately there is already a 2 in the numerator inside the square root. So ultimately we are left with under root km over 2 pi 3 epsilon. I mean basically 2 pi and basically 3 pi epsilon into 2. So basically we are just writing it like this, 2 pi into 3 epsilon. And in the exponential term we have minus km over 2 into 3 epsilon, 6 epsilon. So 6 epsilon we can write 2 times 3 epsilon, and then xp minus xa whole square, same thing. So see here 3 epsilon is corresponds to tb minus ta. So if we substitute tb minus ta in place of 3 epsilon, we get a similar form which we assumed, which we derived, which we got even when we were dividing the path into just 2, I mean for 2 epsilon case also. See, we see no matter in how many equal parts we divide the time interval tb minus ta, whether we divide it into 2 equal parts or 3 equal parts or 4 equal parts or n equal parts, there is a pattern in the integral, in this integral, that integration over all dx1 dx2 dxn minus 1 of e to the minus ks, where s is the this kind of action, right? See, for when we divide it into 3 parts, for 3 epsilon in n equals to 3 case, we have 2 integrations. 2 integrations, like we have this integration, the integration dx1, integration dx2. Now if we divide into 4 parts, we will have 3 integration dx1, integration dx2, integration dx3. Similarly for n parts, we will have n minus 1 integration. That is what we actually have in our general expression, which I have been discussing a lot since the start of the video. I mean this general expression of the kernel, which I already discussed with you in pretty much in good detail, right? This expression I'm talking about. You see, dx1 dx2 till dxn minus 1. For n equals to 2, for 2 parts we are having a single integration, for 3 parts we are having 2 integrations. So for n parts we will have n minus 1 integrations, and that is why you see the integral dx1, integral dx2 and so on till integral dxn minus 1. That is what we have for the general case. Yeah, so right now we see, okay, where were we? We have discussed all of this. Just a second. Yeah, so when n equals to 2, when n was equal to 2, tb minus ta was divided into 2 parts, We got the final integration was under root km over 2 pi into 2 epsilon. We expressed it in this form. Then exponential minus km over 2 into 2 epsilon xp minus x squared. If you don't trust me, you can just check it for yourself. See, we got this. Yeah. Under root km to over 2 pi into 2 epsilon exponential minus km over 2 into 2 epsilon xa minus xp whole squared. That is precisely what I have written here. Xa minus xp whole square or xp minus x whole square doesn't matter because it's a squared anyway. And when n equals to 3 for 3 equal terms, you see we just now we got this result under root km over 2 pi 3 epsilon exponential minus km over 2 into 3 epsilon xp minus x whole square. This thing. So basically it's the same form. This result and this result same form. Just you substitute 2 epsilon with 3 epsilon, nothing more. Or basically if we in this case, since we have divided into 3 equal parts, in that case 2 epsilon was equal to tb minus ta. In this case 3 epsilon is equal to tb minus ta. So if we write it in terms of tb minus ta, then we get exactly the same thing. Even if in n equals to 3 case we get this result, and even in n equals to 2 case we get this result, in terms of tb minus ta. Now if similarly now if we divide tb this interval into n equal parts, then epsilon will be tb minus t over n, and then n epsilon will be tb minus ta. Then we will have integration over n minus 1 variables, x1 x2 to xn minus 1, just now I told you. And in that case my action will be m over 2 this thing m over 2 epsilon summation this, then x1 minus xa whole square plus x2 minus x1 whole square and so on till xp minus xn minus 1 whole square. First thing is a to 1, then 1 to 2 and so on till n minus 1 to b, right? So that is basically is nothing but the summation I equals to 1 to n m over 2 epsilon xi minus xi minus 1 squared, like I already told you. So I equals summation I equals to 1 to, this is the general how we define the action also. I already discussed this a couple of times before. And here, yeah, so x0 is xa, the initial point, and xn is xp, the final point, the end point. And by the same logic, in when n equals to 2, our normalization constant was 1 over a whole squared. When n equals to 3, our normalization constant was 1 over a whole cube. So here the normalization constant would be 1 over a whole to the power of n, because here we are dividing into n parts, dividing the path into n paths. Now in this case the integration will be 1 over a to the power n, the normalization factor, and then this integration, these integrations dx1, dx2 and dxn minus 1 and e to the minus ks. So this also we will get, I'm just by induction I'm just directly writing this, we will get under root km over 2 pi n epsilon exponential minus km over 2 n epsilon xc minus xa whole square. And yeah, we can also write it like this if we just replace n epsilon with tb minus ta. And just extrapolating the observed pattern from n equals to 2 and n equals to 3 cases, we got the same pattern in n equals to 2, and we even rigorously derived the same pattern for n equals to 3. Now we can extrapolate it for n equals to n case also. Now let n tends to infinity, or equivalently epsilon tends to 0. We're just taking the limit to make it more accurate. So in that case, yeah, n epsilon, now see, whatever, even if n tends to infinity, that means we're just increasing the number of parts we're dividing into, but the total n into epsilon will always give you tb minus ta. If n is 2, I mean if I just divide into 2 parts, then 2 epsilon will give you the total time length tb minus ta. If 3 parts, then 3 epsilon. Then similarly, if n parts, if for any arbitrary n, here we are not specifying n, even if n is very large, n tends to infinity, n epsilon equals to tb minus ta will always be valid. So in that case, you see, yeah, so now the net integration we can write it like this, limit n tends to infinity by taking the limit 1 over a to the n. Then we can write it like this, this integration minus infinity, I mean just this thing, dx1, dx2 until and so on to dxn minus 1, and I've just broken this, written e to the minus ks, in place of s I've just substituted this entire action, okay, this entire action. Now we can say with confidence that this integration will be equal to this thing we have derived here, because even if n tends to infinity, tb minus ta equals to n epsilon will always be true. So this is the expression we get. And in usual notation, you see, integral e to the minus ks, we can write it like this, because s is what, the action I defined it is integral l dt, integral ta to limits ta tb, the initial time and the final time, l dt. So that is, this is what I have written, integration t equals to ta up to t equals to tb, then l dt. L is the Lagrangian, which is just the kinetic energy in this case, because for free particle the potential energy is 0, and kinetic energy is half mv square, so half m, and v is dx dt. and x has some dependence on t, so dxt dt whole squared and then dt. So this is integration e to the minus ks, and s is this integration this thing dt. That is what we have written. And here it is just I already told you this capital D notation. This is the Feynman integral. Instead of writing so many dx1 dx2, we just write this capital D x comma t. So this is the same integration. We are just writing this. Just a second. Yeah. So all this so many integration dx1, integration dx2, and so on till integration dxn minus 1 e to the minus ks. That thing we are writing as a single integration and a single capital dxt and e to the minus ks. And yeah, s I have written it broken down here like this here. You may not, the same thing. And yeah, the result we get is the result is the same thing. I already derived it. The result will not change. K over 2 pi this thing. Yeah, just this result which we get. So the LHS, this LHS, if you see, this is actually a sum over paths. This integration, if you see, or this integration, whatever, it's actually we are taking into account all the paths. We are dividing the time into discrete steps, but then we are taking the limit n tends to infinity, and then we are also integrating over all the paths at all the levels dx1, dx2, dxn minus 1. So if n tends to infinity, then this is also increasing. So we are all possible levels, we are taking all the possible x values also. We are integrating over the x values. So this is essentially a sum over paths for a given set of values of x1, x2 and so on till xn minus 1 that define a path. Like this figure which I already showed you. Like for instance in this figure. Where it is just a second. Yeah, this figure. So for this particular this is the particular path. This set of value x1, x2 and xn minus 1, they define this path. Then x1 prime, x2 prime, they define this path and so on. So that is what I have said here. Just a second. Yeah, all of this is done, right? Yeah. Yeah. So for a given set of values of x1, x2 and until xn minus 1, define a path. And for that given path, the integrand e to the minus ks assumes a specific form, a specific value. Yeah, if we know the path, if for a particular path, we can calculate this value. We get a specific value. And for a different set of values of x1 to xn, say x1 prime, x2 prime till xn, xn minus 1 prime, we get a different path. And the integrand assumes a different value and so on. So as we vary the values of x1, x2 and xn minus 1, and that is what we are doing when we are integrating over dx1, dx2 and so on. Basically the integrand essentially gets evaluated for all the different paths. That is why this is what we mean when we say sum over paths. And yeah, keep in mind that the above calculations is for a free particle only. It's no potential. Now again, this part I discussed near the very beginning only when I was discussing the classical limit. Okay, I hope you can recall this vector and all this case 1, case 2 I discussed. Yeah, from here let's again continue, proceed. So b tb comma xb and a ta comma xa. So we have a two-dimensional x versus t space like the space we have been considering so far, the same thing basically. So and 2 points a and b where the coordinates of a is ta xa, time coordinate comma space coordinate, and b tb xb. So the kernel b comma a, we can also write it in this notation k tb comma xb semicolon ta comma xa. That is basically this tb comma xb means b and ta comma xa means a. Basically the same thing as kernel b comma a, and that as we have seen is given by limit n tends to infinity 1 over a whole to the n, this all this integration e to the I over h bar s dx1 dx2 and so on till dxn minus 1. But now we need to evaluate this integral, and it's a pretty daunting, difficult, challenging task. But now we know how to evaluate integral of this form because we have already evaluated this integral. The only difference is that we have done this for e to the minus ks, not I over h bar s. But otherwise we have done this. But anyway, k is a constant. Minus k is a constant and I over h bar is also a constant. So that should not be a problem. Now if you are studying a free particle, we will use the free particle action in place of s, like this action which I already told you. I've been using this a lot of times, this action m over 2 epsilon and this thing. So now we can write this k, this kernel as limit n tends to infinity 1 over a to the n, this thing, and e to the I m over 2 h bar epsilon. Because now we are starting from this form, so I over h bar. So yeah, e to the I m over 2 h bar epsilon, and then this thing. We're just substituting in place of the action s. We're substituting this value, nothing more. Now we previously got, this is the result which is I was talking about. Just now we derived that limit n tends to infinity 1 over a to the n, and this integration for everything is similar except that we have e to the minus k m over 2 epsilon, not I over h bar. And this integration we got this value like this result, under root km over 2 pi tv minus ta exponential minus km xb minus xa whole square over tv minus ta over 2 tv minus t, if I'm not much mistaken, right? I guess it's a mistake. Just give me a second, let me just check it right now. Yeah, under root km 2 pi tv minus t exponential minus km xb minus x whole square 2 tv minus t. This is the, the expression which we have got. Yeah, this is the one. So everything is fine, but it should be 2 here. Okay, let me just write this also. No issues. Just a second. But I mean, just a second. Just give me a second. Yeah. So I'm just writing it. I'm just adding. Yeah. So there should be 2 here. I mean, anyway, that doesn't matter. So this is the result we already derived. Now, if I substitute minus k with I over h bar, I already gave you some hint that this is what we will be doing. Then we get our expression for the propagator for a free particle. Because e to the minus k is, that was not the propagator, the same form of the kernel. But in propagator, we already know it is defined in this way, e to the I over h bar s. But first we did that for ease of calculation, because we know this Gaussian and all for e to the minus k, this form of integrations. Now we will make this substitution, minus k is I over h bar. So 1 over a, first of all, 1 over a we got is under root km over 2 pi epsilon. We already got this previously using that Gaussian function and everything. 1 over a we got. Let me show you still, if you are not convinced. Let me just show you, and let me see myself also, so that I will also be convinced, just a second. Yeah, somewhere here. See, 1 over a is under root km over 2 pi epsilon. We got this here, normalization constant. That is the same thing which I have written here. If you see, if you see, just a second. Yeah. So 1 over a is under root km over 2 pi epsilon. Now, if I put k is minus I over h bar, because minus k is I over h bar, so k is minus I over h bar, then what I get is that essentially 1 by a is under root minus im over 2 pi epsilon h bar. Now minus im. So this, see, I can write it as im over minus 2 pi h bar epsilon. It doesn't matter whether you consider the minus negative sign in the numerator or the denominator. So let us consider in the denominator, and minus 1 is I square, right? I square, I is the imaginary number under root of minus 1, so I square is minus 1 by definition. So we have im over 2 pi I square h bar epsilon. We just removing the minus sign and using an I square in the denominator. So 1 I will get cancelled from the numerator and the denominator, and we are left with under root m over 2 pi h bar I epsilon. Now, if you remember, this is exactly what I told you in the near the beginning, that this is the form of the normalization constant 1 over a. Why is the form? Now we have derived it. Now we are convinced why this is the form. But let me just show you, just in case, that in the beginning, in the very beginning, we assumed that this is precisely this m over 2 pi I h bar epsilon. You see, we assumed this. Yeah, a is 2 pi I h bar epsilon over m to the power half. So 1 by a will be m over 2 pi I h bar epsilon to the power half. This exact same form. We were in page, I guess, 36, right? Not 30, yeah, 36. So you see the same thing. M under root m over 2 pi I h bar epsilon. It's 1 over a. So yeah, and now so in this equation, okay. And now in this equation we need to replace substitute k with minus I over h bar. Let's do that. So see, in this, so we have this under root, this equation is this, right? Under root km over 2 pi tv minus ta exponential minus km xp minus xa whole square by tv minus ta. So we get m over 2 pi h bar epsilon h bar I. See, in place of k I am writing minus I over h bar. So m over 2 pi h bar I. See, because it should be minus im over 2 pi h bar, But in the same way, if we bring the minus in the denominator and write I square in place of the minus, then we will one I will cancel, the I in the numerator will go away, and we will be left with a single I in the denominator. So that's why m over 2 pi h per I tv minus ta. Exponential again minus k. So minus k is just I over h bar. So I over h bar directly m xt minus xa whole square, and then 2 tv minus ta. See again here I have not written, see here this should be 2 tv minus ta. Here also for some reason I have not written the 2 here. But see here I have written the 2 because this 2 where it's coming from. See k minus k, in place of minus k I have written I over h bar. There is no 2 here. And then m xp minus xa whole square, and in the numerator in the denominator tv minus t and 2. So this 2 is there. So this is a mistake here. Let me correct this here also just in case. Oh shit. It's very difficult to scribble like this because I'm using this touchpad of my PC. I'm not even using a touch screen or whiteboard or iPad anything. So anyway, yeah, just I think you understand it. Just so that I don't this mistake is glaringly obvious. That is why let me just mark it here. I think you can understand it, right? So ultimately we get this thing, replacing k in this equation we get this, and so then we can write that this kernel, this was the expression for the kernel, right? So kernel b comma is this thing, under root m over 2 pi h per I tb minus ta into exponential this thing I m over 2 h bar xp minus x a whole squared over tb minus t. And this is nothing but the kernel for the free particle k naught b comma I, because we have done all the calculation assuming it's a free particle. And we can also write this as this thing in place of tb minus t we can write n epsilon. Here I have written small n or capital N, doesn't matter whatever you write. So we can also write it in this form, just n epsilon in place of tb minus ta. So note that we use the action for the classical path. Of course, in place of action we used what? That half mv square, I mean half m by 2 x dot square or m by 2 dx dt squared and all those things. So that is the classical action. We use the classical formula for kinetic energy. And so see, we use the action for the classical path, but yet upon evaluating the path integral we get this thing. So you see k0 b comma is proportional to some constant, which is this entire thing, which I am not going into right now. I mean, in this expression I have not explicitly written the constant. So but this is what I want you to understand. It's very important point actually, that the kernel is proportional to some constant times exponential e to the I over h bar s naught, where s naught is the classical action for the free particle. See, e to the I over h bar, otherwise you see what is left, m over 2 xd minus xa whole square over tv minus ta. See, m by 2, that means m by 2 m v square by 2 is kinetic energy, right? And since it's a free particle, so this should be the action, I mean this should be the Lagrangian also. Okay, let me show you. In the time interval epsilon, let me clearly show you why I'm saying this. See, in the time interval epsilon, okay, this video is 2 hours 20 minutes and we are 38 pages. Okay, I think it's good going because the last part, the major calculation is over. One more major calculation is remaining, that is the Schrodinger equation for free particle. Otherwise, good going. I think I can cover this in maximum 3.5 hours maximum if things if we progress at this rate. I hope I was not too fast. I hope you understood all the points. I mean, if you pay attention and if you have a basic knowledge in mathematics, I don't see any reason why you should not understand. Anyway, so in the time interval epsilon, and epsilon is just ti plus 1 minus ti, the spacing between two successive time intervals, and then is corresponding to xi plus 1 minus xi. Then the particle's velocity is what? Velocity is the dx dt. So the distance, the change in the distance, that is dx is xi plus 1 minus xi over dt, and dt is just epsilon obviously. So velocity v is xi plus 1 minus xi over epsilon, and kinetic energy is of the particle is half m v square, half m velocity square. So half m this thing squared, so xi plus 1 minus xi squared over epsilon squared. Potential energy is 0 as free particle. Now the action is what? Suppose now we are looking at this particular time interval ti to ti plus 1, because see the speed wave assumed xi plus 1 minus xi. So that means we are dealing with, right now we are only focusing on this particular time interval ti to ti plus 1. So in this formula for action, the integration limit will be ti up to, and ti plus 1. k minus pe dt. So k dt since p is 0. Now dt is just epsilon, right? Because yeah, dt is epsilon obviously, and this integration k dt is just k into epsilon. There is no need of any integration or even summation, because see, I mean, anyway, think of it this way: integration ti plus 1 k dt. So the integration is with respect to time, but in this expression for kinetic energy, there is no time variable. I mean, epsilon is a constant; it's a constant interval, and xi plus one minus xi. I mean, there is no time variable. So k will come out of the integration, and we are left with integration ti to ti plus one of dt. That means basically k into ti plus one minus ti. That is what we are left with, right? But what is ti plus one minus ti? That is epsilon. So we are left with k into epsilon. I mean, that is the actual exact reason, right? So action is k into epsilon, which is m over 2. I mean the kinetic energy expression, m over 2 xi plus 1 minus xi square over epsilon squared, that is mv square by 2 into epsilon. So 1 epsilon will cancel, and ultimately we are left with the action is m over 2 epsilon xi plus 1 minus xi squared. This same form we got in all our cases, right? That is why now you look at this expression. Come back here. Exponential I over h bar, just separate the I over h bar. Other than that, we are left with m over 2 epsilon. T minus t is epsilon. See, here we looked at only a single interval, ti plus 1 minus ti, but in general, this is what in general tb minus t is epsilon, this same form, and we have here xb minus xa. Here we have xi plus 1 minus x. I just showed you the general form. So that is why we can say that this m over 2 xb minus xa whole squared over t minus t, this is just the action for a free particle s0. So now we see that this expression which we derived after calculating all this integration using so many mathematical techniques and everything, this complex looking expression under root m and everything, actually this is just that saying that this kernel k naught b comma a is proportional to some constant times e to the I over h bar s naught. And this was the assumption. This was the kind of we assumed that this contribution of the path, I mean the kernel should be of this form, e to the I over h bar s naught, a propagator of the kernel, whatever you call it. So I mean everything is kind of fitting into place at this point, right? And I hope you're enjoying this trip into the world of path integrals so far. Yeah, I know it might seem daunting initially, and yeah, because you are kind of assuming you do not know all of this previously, you're kind of seeing all of this for the first time. So I know it will most likely not be enjoyable, but I didn't learn all of this in a single day in by watching a 3-hour video. But yeah, I didn't find any video or any online resources which explain the topic in this much detail and without any step jump or so. So I think this will be helpful, because I took a lot of effort on my part to prepare this PDF, and right now you see it's in the I don't know if you can see this part of my screen, but it's 2:26 a.m. So it's 2 in the night, and I'm kind of making a video and shouting my head off. I mean, not shouting, but whatever. Anyway, so now see, basically we got this for this interval I to I plus 1, we got this for the expression of the action. Now if we add up all such action for all i's for all the intervals, we get this discretized free particle action s, which we assumed. And since we use the classical kinetic energy expression in the Lagrangian, we can say this expression for s is the classical action s naught, right? Because see, in the Lagrangian we use the classical expression, so this is the classical action, and since we assume Pe or the potential energy to be 0, we can say that this is the classical action for a free particle S naught. So yeah, this thing again, K naught Ba is proportional to some constant times e to the I over h bar into S naught. Now the classical path corresponding to the classical action S naught has the maximum contribution to the kernel, obviously. Already discussed this. Here's a bit of a summary which I can skip, or let me just glance through this once pretty quickly. The propagator k is defined, kb comma is defined as Feynman's path integral as follows: that this is a limit n tends to infinity 1 over a whole to the power n, and then all this integral dx1, integral dx2, and so on till integral dxn minus 1 e to the I s over h bar, where s is the discretized action and 1 over a is this thing. Under root m over 2 pi I h bar epsilon. Epsilon is tb minus ta over n. N is the number of parts we have broken the time interval into, and ta and tb at the endpoints. And this normalization constant, this form, it actually applies for free particle as well as other actions as well. So it's a very general result. I mean, we have just derived this action, this normalization factor using some assumptions, some Gaussian function, but in general this holds in a lot of cases, not just for the present case. This form, this under root m over 2 pi I h bar epsilon. So yeah, anyway, the propagator k naught b comma a is this under root m over 2 pi h bar I tb minus ta e to the im xp minus x whole squared over 2 h bar tb minus ta. This thing we derived, just a summary. This is just a summary part. And this propagator correctly gives the probability amplitude of a free particle going from xa at time ta to some point xb at time tb. I already told you this propagator or kernel, whatever they corresponds to the probability amplitude. And so we have basically divided a path into n discrete line segments on the x versus t space, and the contribution of the ith line segment to the path integral is 1 over a e to the I over h bar m over 2 epsilon x I plus 1 minus xi squared. In general, this is for the ith line segment. I mean, see, there are like I showed you in the diagram, this path, then this path, many different paths. So for different i's, so say the first path for this set x1 x2 to xn minus 1, then the second path is for x1 prime x2 prime, and then and so on and so forth. So I mean, there are many different i's, right? So basically this is right in general for the ith line segment. Sorry, I'm not that I mean, basically see, for from x1 to x2, then x2 to xn on, basically the contribution of the just a second. I mean, I know I'm just talking about the. I mean, let's not get deep into this because it's. I mean, you might get confused. It's nothing new in this. Basically, it's saying that for the ith path in general, we can write that this action is xi plus 1 minus xi squared. For this particular interval, I already showed you, right? This action xi plus 1 minus xi. In general, that is what is written here, nothing more. And that is, yeah, you can write 1 over a e to the I si over h bar. But si is the action for that ith path only. Si is the action corresponding to the ith line segment of that particular path for that particular set of xi values. So yeah, you have for particular set of xi values, say x1, x2, x3, x4, and then the ith line segment means suppose x2 to x3. Suppose this is your ith line segment, then I is your 2 and I plus 1 is your 3. So in that case, for if you want to find the contribution of the ith line segment in that path, contribution of just that portion x1, x2 to x3, then you set I equals to 2 and then I plus 1 will be 3, then you use this formula. 1 over a e to the I over h bar m over 2 epsilon x3 I plus 1 is 3 x3 minus x2 squared. And note that this I is the index, free index, which is the summation index. But this I here is the imaginary number. I please don't get confused, but yeah, it's obvious. It should be obvious. This I is the imaginary number. I should have used j or something, but yeah, anyway, this I is not the same as this I. Okay, so yeah, that is what I have written in. SI is the action corresponding to the ith line segment of that particular path for that particular set of xi values. I mean, let me just quickly show you this figure so that you, otherwise I know it sounds a bit confusing if I just say it like this. Even I got confused a bit in the middle, because I like kind of, I am also new to this path integral, and it's not at all easy topic. I mean, I gave it an effort, and I could understand the topic at a basic level. I mean, whatever I'm sharing with you, that much, and a little more I've also. But yeah, all of what I know I'll not be sharing in this video. Even this video is almost 2.5 hours long. But yeah, in general. But anyway, see, suppose for this particular path, this set of I values, suppose this path x1, x2, xn minus 1 and so on. Suppose I want to know this the contribution of only this line segment x1 to x2. That is what I mean there. Or say for this path x1 prime, x2 prime. Suppose I want to know the contribution of this line segment x1 prime to x2 prime. That is what I'm talking about. This is anyway some important points I've written there as part of a summary. It's not important. This is not really important because I'm not preparing you for any kind of exam on path integral. I'm just giving you a general. Trying to give a general understanding of the subject. Right. So yeah, all of this we have already covered. We have covered all of this. Perfect. Yeah, here summary. So under the summary, I was in the summary, right? We have just discussed some points. So see, 1 over a e to the I over h per m over 2 epsilon x I plus 1 minus xi squared. This thing, it is actually the infinitesimal time free particle propagator. It's a free particle propagator, but for infinitesimal time, because xi plus 1 minus xi. So for the single time step, and ideally epsilon tends to 0 or n tends to infinity. So this is for the infinitesimal time. This propagator, and this is denoted by ti plus 1 comma xi plus 1 semicolon ti comma xi. Okay, this kernel. Basically, the probability amplitude of the free particle to go from ti comma xi to ti plus 1 comma xi plus 1, infinitesimal time interval. So then there is this thing called the finite time and infinitesimal time free particle propagators from this thing. Infinitesimal time free particle propagator we just now discussed. So finite time free particle propagator between the space-time points A and B, Ta, xa and Tb, xp is the particle's probability amplitude to go from A to B. So this path consists of the points Ta, xa, T1, x1 and so on till Tn minus 1, x and n minus 1 and ultimately Tb, xp. The first and last points are fixed, but by changing the intermediate, of course I told you, TAXA and TBXP, the first and last points, A and B, they are fixed. And but by changing the intermediate points from 1 to n minus 1, we can get different paths. And that is why we integrate over all these things to get the complete sum over paths. So yeah, by changing the intermediate points, we can get different paths between A and B, and all such paths contribute to the calculation of the free particles probability amplitude to go from A to B. Now for an infinitesimal time interval ti to ti plus 1, there is only one possible path, because see, by definition it's an infinitesimal time interval. So to go from, I mean, very small amount of time, almost like infinitesimally small amount of time. So you don't have, I mean, that means there is just only one path connecting ti to ti plus 1. Just, I mean, that is by definition, because see, there is only one possible path, because in between ti and ti plus 1 we cannot divide, we cannot define any point like we did. You remember for the multiplicative law of propagators, we took a and b, the endpoints, and we defined a point c in between. But we cannot do that because ti and ti plus 1, that means they are two successive time steps. We have divided the time step into a very small epsilon, and ti plus epsilon is ti plus 1. So we cannot by definition we have not divided into any shorter interval. Epsilon is the shortest time step. I mean, in definition, like I've written there, if we divide the interval ti, ti plus 1 further, then basically the new smallest interval becomes the infinitesimal time interval. But I mean, we cannot go on doing this infinitely. By definition, ti to ti plus 1, there is only one possible path. You understand, right? Because yeah, there is only one possible path, because there you cannot, you don't have a law, you cannot define points in between. So the free particle propagator is this thing which I already derived, and if we take the mod square of this, then this can also be written as the mod square means what? If we have a complex number a plus ib, what is the complex conjugate of a plus ib? Complex conjugate means we just change the sign of the imaginary number I, that is a minus ib. Now if I multiply with the complex conjugate of this complex number a plus ib with the number itself, that means a minus ib times a plus ib. What I get is that, see, a plus b, a minus b is a square minus b square. So that means a square minus I square b square, but I square itself is minus 1. So a square minus b square, that means a square plus b square. So if I multiply the complex conjugate of a complex number with the number itself, I get a positive quantity. A square plus b square is always positive, because there are two terms, a square and b square, and both of the terms are square terms. They are always positive. And a plus ib is the general form of a complex number. Okay, it's just an arbitrary case. And if I take the mod square of a complex number, see, essentially taking mod square means for a complex number, taking mod square means just taking this thing. Okay, this summation, this complex conjugate into the number itself. So this kernel b comma a mod square equals to this thing, which is what? See, look at you understand. Let's try to understand one thing. What is this kernel? It's a probability amplitude. This kernel is basically, after solving all these integrations and everything, we get this expression. But what is this? See, under root m over 2 pi h bar I tb minus ta. So when we are solving a real world problem for a particle, free particle, we know the mass of the particle. So we know m, we know 2, we know pi, we know h bar, we know I. All of these are constants. And we know tb minus ta, we know the end points, right? Then exponential I, m, we know the mass, xp, xa, tb, t, all of these are known, the end points, and h bar. So everything in this expression is known. So, and basically there is this imaginary number I. So e to the I something can be written as, can be expressed as a complex number. You see, this is basically a complex number expressed in polar form. That is, this is the amplitude, this under root term, and then e to the I something. So e to the ix is it's like r e to the power I theta. In complex analysis we do, even in high school level we do, right? So that is the polar form representation of a complex number. We can also represent it in form of a plus ib, the Cartesian form, right? If you break e to the I theta into sine theta plus cos theta plus I sine theta, and then this cos theta sine theta, if we can find the equivalent representations, so we can do that. So basically this it should be clear to you that this k not b comma this kernel is nothing but a complex number. And if we take the mod square of that complex number, that means we are essentially multiplying that with its complex conjugate. And by doing that we get this. How? Because see, what is the complex conjugate of this kernel? First let us consider the exponential term. See, the I will become minus I, and rest m xp minus xa whole square over 2 h bar tb minus ta, this thing, everything will remain the same. So if I multiply e to the ix into e to the minus ix, ultimately they will cancel to give 1. So just forget the exponential terms. And as for this under root terms, see, this term under root m over 2 pi h bar I tb minus ta, and if I take the complex conjugate, then will be under root m over 2 pi h bar I tb minus ta minus, this should be minus sign basically because minus I, and both under root. So if I just multiply them, then we will just I'll just be left with this thing here. You see, m over 2 pi h bar tb minus ta. Right? Why? See, if we are multiplying under root into this into under root that. So when we are saying under root m over in the second case, in the complex conjugate, it is under root minus m over 2 pi h bar I tb minus ta. So that means minus m means I square m, and I with I square, if we just do the cancellation, I am left with under root I m over 2 pi h bar I tb minus ta, the complex conjugate part, under root I m over 2 pi h bar tb minus ta. In this case, no I in the denominator, we have already cancelled that. So we basically have under root, first the complex conjugate of this thing, under root I m over 2 pi h bar tb minus ta into under root this thing itself, m over 2 pi h bar I tb minus ta. So that means if we just bring this term together as a product under a single square root symbol, one I in the numerator will cancel this I in the denominator, and we are left with this same thing, m into m square over 4 pi square h bar square tb minus ta whole square under root. So that means the square term under root. So ultimately we are left with m over 2 pi h bar tb minus ta. And you see, this is a positive quantity, tb minus ta is a time interval, cannot be negative, h bar is a positive constant, pi is also a positive constant, and m mass also cannot be negative. So this is the probability, a mod square of a kernel, right? This is the probability of the free particle moving from the point ta comma xa to the point tb comma xp, and we see that this probability does not depend on the space variable x. You see, this m over 2 pi h bar tb minus t, there is no dependence on x. Although the particle starts at xa at time ta, it is equally likely to for the particle to end up at any position in space at some later time tb. It's a very important observation actually, because this probability does not depend on x. Right? This is obviously in quantum mechanics we cannot predict where the particle will end up. Okay. Now we will quickly show how the de Broglie relation, de Broglie relation, which is h over p equals lambda, and Planck's quantum equation E equals hf, how both of these relations can be derived from the free particle propagator. We will only be deriving this for the free particle, not for more complicated cases. And then finally we will discuss we will derive the Schrodinger equation for free particle using the free particle propagator, and we will finish this video. We'll end up with this video. So the de Broglie relation using free particle propagator. So this is the free particle propagator or the kernel which we already derived. Now you see, without loss of WLOG means without loss of generality. In many mathematical proofs you will see it means without loss of generality. That means we just setting x equals to 0, ta equals to 0, xb equals to x, tb equals to t. We are not assuming any special case. We are retaining the generality. We are without any loss of generality, but we are just substituting x. We are assuming that we are starting from the point 0, 0. See, origin you can shift, it's your wish. So we are assuming xa comma ta equal to 0, 0, and xb equals to x and tb equals to t. So then we get this thing equal to m over 2 pi h bar I t, because tb is t and ta is 0. So tb minus ta is just t. Then exponential I m xb is x and xa is 0. So xb minus x square is just x square, and over similarly 2 h bar t. So this thing we have under root m over 2 pi h bar I t exponential I m x square over 2 h bar t. So and this is the probability amplitude of the particle going from 0, 0 to t, x as per our notation in the space-time diagram. Now we plot the real part of this thing. Suppose we multiply under root I with this above expression, this kernel and then this is definitely a complex number. So a complex number means it is a real part and the imaginary part. A plus IB. A is the real part and B is the imaginary part. So suppose we plot the real part of this thing, not just the kernel, we plot the real part of this entire thing, under root I multiplied with this kernel as a function of position, as a function of x, and here we obviously treat the time as fixed, for a fixed time. So at a fixed time we are just varying the position and we are seeing how this kernel, the real time of the kernel varies. Then we get this kind of graph. I mean, this is the nature of the plot. Now it's not exactly clear to me why we plot exactly this function and all, but this, but yeah, usually if we plot it in any software and see, this is the nature of the graph, and how we are, and what is this telling us is that, you see, this is 0 and this is minus 5, and this is like, oh, this is plus 5, I'm sorry, this is plus 5. Okay, so basically at 0, I mean x equal to 0 means what? See, from here one thing we can say is that the distance between the nodes of this periodic function, this function is periodic more or less, at a short level, we can treat this function to be periodic. I mean, yeah, it's definitely the distance between the nodes of this periodic function stays relatively constant over a few cycles for large x. See, for large x means, see, for 5 may not seem to be a large number. I mean, just ignore this value 5. Basically, when we're moving far away from 0, here this is the origin 0. The origin is not here, okay? Origin is here 0. So if you're moving far away from the origin, to the left or to the right, doesn't matter. We see that here the graph is like this. So it's more or less it's relatively constant. The distance between the nodes. See the distance, it is this and this. But here, see the distance, it is a huge distance. Then huge. I mean, it's not constant. But as we're moving far away from the origin, the distance between the nodes remain relatively constant. And one thing we can see is that we see the wavelength is short at large x, where a classical particle could arrive only if moved with a high velocity or high momentum. See, large x means what? X means position, right? So large x means what? We are moving very far from the origin, towards the left or towards the right. But that means you need to accelerate the particle. The particle should have a very high momentum to be able to cover this much distance, right? But you see, at large x, we see the wavelength is becoming very small. You see, the wavelength is short. Wavelength is what? This is the wave. Suppose this is the wave. You see, this is the wave. So it has a long wavelength. Now, if the wave is like this, it has a short wavelength. Wavelength is the distance between the adjacent peaks or the crests and troughs. So see, in these regions, the wavelength is small when we are moving far from the origin. But at the origin, it's a large wavelength. So what does this mean? Basically, we see wavelength is small or short at large x, because for large x means a classical particle could arrive at large x only if it's moved through high velocity or high momentum. So that means high momentum corresponds to low wavelength. Here only we are getting an intuitive feel of de Broglie's relation, that h over p equals to lambda. P h divided by p is lambda. So lambda, or the wavelength, is inversely related to the momentum. Classical momentum and the wavelength are inversely related, canonically conjugate variables. Momentum and wavelength. Wavelength corresponds to position, roughly speaking. And Heisenberg's uncertainty principle also says the same thing, that you cannot know both the position and momentum of a particle with 100% accuracy. Yeah, you can arrive at de Broglie's relation using experiments and using Einstein's equation, the usual way that is taught in college courses. But here I am showing that using the free particle kernel also you can arrive at the same relation. So let me show you how. So to calculate the wavelength lambda, we assume x to be large and replace x, because we just assume x to be large. The x to be large means we are finding the lambda at a very away from the origin, and replace x in the expression for the kernel by x plus lambda. Because see, since x is large, why we are assuming x to be large? Because only if x is large, see, I have written here that only if x is large, then the wavelength is short. So only if x is large, then I can approximate, then lambda will be small. If x is large, the wavelength lambda will be very small. So large x, if x is large enough, then I can say that x is more or less equivalent to x plus lambda, because lambda is small in that case. Only then we can make this substitution, that x, we can substitute x, replace x with x plus lambda, only if x is large and in turn lambda is sufficiently small. So then we get a new kernel, say k naught prime b comma a, in which we set equal to the original kernel. Because see, since why we are setting equal to the original kernel, because x is equal to x plus lambda for large x. So if we substitute x with x plus lambda, then it should the new kernel should be equal to the original kernel. What is the new kernel? See, this was the kernel expression we had. So here the same, everything will be the same, but except in this x square we will write x plus lambda whole square. In place of x we will writing x plus lambda. So k naught prime will be this thing, everything is same, but here we have x plus lambda whole square, and if this is equal to k naught, that means we have x plus lambda whole square, this expression should be equal to this. So this constant term cancels and we are left with exponential I m x plus lambda whole square over 2 h bar t is equal to exponential I m x square over 2 h bar t, and multiplying both sides by exponential minus I m x square 2 h bar t, we get this thing. See, this thing we have now, we are multiplying both sides by just a mathematical trick manipulation, exponential minus I m x square over 2h bar t, just the minus. Okay, we are multiplying both sides, so that means the right hand side will become 1 because we have e to the I m x square over 2h bar t, and we are multiplying with e to the minus I m x square over 2h bar t, and the left hand side will become, we had I m x plus lambda whole square over 2h bar t, this thing, and minus e to the a into e to the b is e to the a plus b, or whatever, e to the a, e to the minus b is e to the a minus b. So here left hand side we have e to the this entire thing, this thing minus this thing, I am x square over 2h bar t, and this is equal to 1. Now we know e to the 2 pi I equals to 1, e to the I into 2 pi is, because is cos 2 pi plus I sin 2 pi, sin 2 pi is 0 and cos 2 pi is 1. So this is e to the 2 pi I is 1. So in place of 1 we can write e to the 2 pi I. Now in both LHS and RHS we have exponential. So we can equate the arguments of the exponentials and we can say that 2 pi must be equal to this thing in the second brackets, I m x plus lambda whole square over 2h bar t minus I m, minus I m x square over 2h bar t should be equal to 2 pi I in that case. But yeah, we can cancel the I from all the sides, and we are left with, if you just cancel the I, we are left with m x plus lambda whole square over 2h bar t minus m x square over 2h bar t equals to 2 pi. So now you see, if we just break x plus lambda squared, m x square plus lambda square plus 2x lambda over 2h bar t minus m x square over 2h bar t equals to 2 lambda. Now m lambda square plus 2 mx lambda over 2h bar t equals to 2 lambda, because you see m x square by 2h bar t and we have a minus m x square over 2h bar t, so these two terms will cancel. Ultimately we are left with this. Just this part is just high school algebra. Now since lambda is very small, x is very large as compared to lambda, we can ignore lambda square. Lambda square can be neglected, and thus we ignore this term m lambda square. So we are left with 2 mx lambda over 2 h bar t equals to 2 pi. In the LHS, the 2 in the numerator cancels the 2 in the denominator, and x over t, what is x over t? X is the displacement and t is the velocity. It is the time. So x over t is the classical velocity, displacement over time, right? V. Since x is very large, we can use the classical expression here. X is very large, so it's in the classical limit. X greater than lambda. So that means mx lambda over h bar t, if we write x over t as velocity v, we get mv lambda over h bar is equal to 2 pi. Now what is, so mv equals to 2 pi h bar over lambda, right? And h bar is the reduced Planck's constant, which is h over 2 pi. So that is 2 pi over lambda into h over 2 pi. So we can cancel the 2 pi's and we are left with mv equals to h by lambda. And what is mv? Mv is the linear momentum, mass into velocity, p. So we are left with p is equals to h over lambda, or h over p equals to lambda, however you write it. That is the famous de Broglie relation, which connects the wavelength lambda of the quantum wave associated with the particle. Wavelength lambda of what? What is the wave here? That is the matter wave concept, de Broglie's concept of matter wave. That is the quantum wave associated with the particle. So it relates that with the particle. This is quantum wave associated with the particle of mass m, which is moving with velocity v. So it relates that wavelength with the particle's linear momentum p, and it shows this wave particle duality, because linear momentum is kind of a particle concept, roughly speaking, and lambda is kind of a wave concept. So here it's although it's not a rigorous, we kind of showed that we can arrive at de Broglie's result using the propagator, using Feynman's approach, path integrals, for in the classical limit, if x is very large, only then we can clearly show this, right? Now give me 1 second, I'll just plug in my PC, okay? Because it's showing low battery. I'm not pausing the video, it will just take me 2 seconds. Yeah. Yeah, I'm back. Okay, perfect, fine. I hope you can hear me and everything. The video is 2 hours, 3 hours, okay. No, I guess it will be a 4 hours video. I cannot cover it in 3.5 hours, I guess, because still the Schrodinger part is left. But yeah, let's keep moving. So now I will show you that how you can arrive at Planck's quantum equation equals hf using the for a free particle using the propagator, using the free particle propagator. So now let's plot this part, real part of this same thing, under root I k naught b comma as a, but now we are plotting it as a function of time. This time we are plotting it as a function of time, and we are giving the fixed x. We are fixing a position x, and we are seeing how this propagator, I mean how it varies with time. How this expression, this propagator, this kernel, whatever, it varies with time. Even if the position is fixed, it might vary with time, right? Because the kernel, it has a lot of it has some dependence on time, if you think about it. And in this case, what we did is that we were keeping the time fixed, and we are seeing how it varies with position. The kernel obviously has a dependence on position also. And in this case, we got this kind of graph, this kind of plot. Here, the plot looks like this. A shape of this is kind of like the damped oscillation, kind of, but not exactly similar. I mean, it's a hand-drawn one, so I mean, I'm sorry for this, but it's, yeah, you get an idea, right? Here we are plotting it with respect to time. So here you see from this plot, what we can say is that the amplitude of the function falls off. For actually, this should be capital F here, falls off with increasing time. See, as time is increasing, the amplitude is decreasing. But when t is large, I mean at very large time, the amplitudes are relatively constant over a few cycles. And the plotted function behaves like a fixed amplitude sinusoid. See, when for large t, see at this point it's almost a fixed, I mean here it's varying more rapidly. Here it's coming up to here, here, up to here, here. So that is the thing, is that for large t, when t is large, actually I cannot, it may not be clearly evident from this plot. It's a hand-drawn plot. But yeah, when t is large, the amplitudes are relatively constant over a few cycles. I mean, it's not like it's constant for forever, but yeah, they change very slowly. So over a few cycles, for a few cycles, they are more or less constant. But here, see, even in this small distance, it's changing so much. But here, it's changing, but up in a huge distance. So for a few cycles, it's more or less constant. That is the basic idea, right? And the plotted function behaves like a fixed amplitude sinusoid in that region. Thus, we can say that k naught, this kernel for this free particle kernel or propagator, approximately repeats itself if t is large. So if t is very large, then it repeats itself. It's kind of periodic. Now let the time period of the kernel be t, capital T, which of course we assume to be much less than small t. See, what is capital T? Capital T is the time period of the kernel, in the sense it's the actual time period. See, I have explained it. The time period of oscillation of kernel, capital T, is the time needed to decrease the phase by 2 pi. Decrease the phase by 2 pi means you are basically kind of coming back to where you started from, coming back to your initial state. So the time taken to come back to your initial state, that is what we mean by the time period. In this case, time period of oscillation. That is the actual time period. The time period of oscillation of the kernel, capital T, this is what we denote by capital T. It is the time needed to decrease the phase by 2 pi. Decrease because here it's decreasing. And this, but if small t is the variable which we are plotting along the horizontal axis. So if t is large, yeah, it more or less repeats itself. But now you see, this is the capital T is the time period of the kernel, and we assume that capital T is less than t, because yeah, see, when t is very small, then capital T is what the time period for the kernel, I mean for this function to repeat, for the kernel to decrease its phase by 2 pi. So it will take a very small amount of time to decrease the phase by 2 pi, because it's this capital T, I mean our motivation is that small t should be very large. Only then we can assume that the function repeats. But the time period is constant. It's not like it cannot be indefinitely large. So here we study time dependence of the free particle kernel. We basically hold the distance fixed and vary the time, both the frequency and amplitude. Yeah, anyway, since probability amplitudes are almost constant for large t, that is our assumption, and since t is much greater than capital T, when I say t, you take that to mean small t, and otherwise I will explicitly say capital T. So since t much greater than capital T, then t plus capital T is approximately equal to t. So we can equate, we can say that under root m over 2 pi I h bar t e to the im x square over 2 h bar t, that is the free particle propagator which we got, is equal to m over 2 pi I h bar t plus capital T e to the im x square over 2h bar t plus capital T. I mean, just basically we have substituted t with t plus capital T because capital T is very small. And since t is much greater than capital T, t is approximately equal to t plus capital T. So we can write this. Yeah, this is the same thing which we did above. Now this just a second. No, this is not the same thing. Now since t is approximately equal to t plus capital T, we can write m, this under root m over 2 pi I h bar t as under root m over 2 pi I h bar t plus capital T. But that will not make any difference, right? Just a mathematical trick, nothing more. So that means in this constant, in this place, we are just substituting t with t plus capital T, and now we can cancel these constant terms here to make our calculation much more simpler. So now we are left with just two exponential terms. E to the im x square over 2h bar t is equal to e to the im x square over 2h bar t plus capital T. Now we multiply both sides by the similar trick we used previously when we were trying to derive de Broglie relation. We multiply both sides by e to the minus I mx square over 2h bar t plus capital T. And then we get, yeah, in the RHS we will have 1 obviously, or e to the 2 pi I. And LHS we will have e to the I mx square over 2h bar t minus I mx square over 2h bar t plus capital T. So thus we can again equate, and you can just cancel the i's. We ultimately will have in the similar way mx square over 2h bar t minus mx square over 2h bar t plus capital T is equal to 2 pi. So up to this, I hope it is clear to you. Now see, I hope it's clear to you. This point is, I think I didn't make this part of the argument convincing, that why capital T must be much less than small t. Actually, we should say the other way around. Small t we have assumed to be much greater than capital T, because it's important to understand what capital T actually is. When we say that capital T is the time period of what? Is the time period of oscillation of the current. Oscillation means what? You're oscillating once, so suppose you start from here and you oscillate and you come back to here. So suppose it starts from here and it comes back to here. The time taken for this is the time period, roughly speaking. One complete oscillation. Then from here to here is one complete oscillation time period. So basically it's obvious that this capital T is much less, because when near this region of the graph, this capital T is much less. It's obvious time period. But small t we're assuming it's very high, because only then we can more or less treat it to be a constant function, because the graph is, if possible you can see this full plot. It's let me just show you if in my Feynman heaps, if it's possible for me. Just a second. I have this graph in Feynman heaps actually. Just give me one. Just give me a single second. Let me just. Yeah, am I audible? Right. Okay, so you see, this is the diagram from this Feynman Heaps book, the third chapter, developing the concepts with special examples. You see, this is this diagram. You see, it's kind of see at this point it's changing very rapidly. So capital T is small, but at a very large T we can see it's more or less it's changing very slowly. I mean, you get the rough idea. This calculation is done here also, which I'm currently showing you. They have done it in a slightly different way. They have not the same thing basically. E equals h bar omega. I will just derive E equals hf, which is the same thing. And then they have actually even fundamentally got into more deep, which I will not be able to do in this video. And diffraction. Anyway, let me just close the book. And the previous graph which I showed you for the when we were deriving the de Broglie equation, momentum and energy. You see, we get this result. Lambda equals to h over p. You see, get this result 2 pi h bar, that is just h, because h bar is h over 2 pi, h over m v, x bar t is v, so mv equals h over lambda, whatever. So see, all these things I discussed with you. You see this form of this path integral, this is the c, the intermediate point, all these things. Anyway, but yeah, like you see here, the rule for two events. Here they have simply not derived this. They've just shown you this, like kba is equal to this some product of these two kernels and integration over dxc, but they have not derived it rigorously. I showed the rigorous derivation. Then let me show you in chapter 3. You see the free particle. They have just directly written this form, that the free particle propagator is m over 2 pi I h by tb minus ta under root exponential im. This thing I derived. This was a pretty long derivation. You see, they have not derivation. The calculation is carried out as follows. Notice first that this is this. Next we multiply this result and integrate again. they have just written that we integrate, but they have not actually carried out the integration. And this integration is, as you know by now, it's a pretty tough integration. So and then they have written this thing. So to come to here, just a few lines in Feynman heaps, but to make sense of this, it took me almost one whole day. But yeah, that is why I'm making the video, because I think it will be helpful to some of you. Because I have not skipped any portion. I've shown you all the mathematically rigorous derivation, right? Yeah. So anyway, where was I? Okay. So now, so we have come till here. Mx square over 2h bar t minus mx square over 2h bar t plus capital T equals to 2 pi. So you see, in this term we have a 1 over t plus capital T. Now 1 over t plus capital T can be just a simple mathematical trick. It can be written as 1 over. From the denominator, if we take t common, we can write 1 plus capital T over t, or we can write 1 over t, and this thing we can write 1 plus capital T over t inverse, right? Just this thing inverse. So 1 over t into, now see, since capital T is very small in comparison with t, and using this binomial rule, we can say that 1 plus capital T over t to the power minus 1 is just 1 minus capital T over t. I mean, I've just used the result that 1 plus x to the power n is equals to 1 plus nx if x is sufficiently small. So then 1 over t plus capital T we can write, we can approximate it as 1 over t into 1 minus capital T over t. So similarly we had this thing here. Now in place of this thing we can just write here 1 minus capital T over small t here, and 1 over small t here, so that small t is here. So mx square over 2h bar t minus mx square over 2h bar t into 1 minus t over 1 minus capital T over t equals to 2 pi. Now just break this term, so you will have this minus this plus minus minus, so plus mx square capital T over 2h bar t square equals to 2 pi. So these two terms will they just cancel out, and x by t equals to v, so x square plus by t square, x square over t square is v square. So we have mv square t by 2h bar, mv square t, nv square capital T by 2h bar is equal to 2 pi, right? That's what we have. So mv square by 2, that is just the kinetic energy, right, is equal to what? 2 pi h bar over t. Now what is h bar? Is h over 2 pi, so that means we can just cancel the 2 pi and we are just left with h over t, and this t is the time period. So the reciprocal of the time period, or 1 by t, is the frequency f. So that means mv square by 2 we get hf, or the frequency. So now mv square by 2, see, since it's a free particle, this particle we need to take into account only the kinetic energy, right? So mv square by 2 is just the energy of the free particle. So we have E equals hf, the energy equals hf. And if you want to write h bar omega, so what is h bar? H bar is h over 2 pi. So just divide by 2 pi the RHS, and you need to also multiply by 2 pi. So omega is 2 pi into frequency. So 2 pi f is omega, and h over 2 pi is h bar. So you can write equals to h bar omega as well. Or even here, if you see, just you already have a h bar, and 2 pi by t is omega by definition. So h bar omega. Right, now finally let's move into the last part of the video. It's let me see how much time it's taking. It's 3 hours 6 minutes. Okay, let's see. Now we will derive the Schrodinger's equation for a free particle using the free particle propagator and Feynman's path integral approach. So Schrodinger's wave equation, see, it can be guessed or derived. See, Schrodinger's wave equation is by itself a very fundamental and interesting and important topic in physics, and I have discussed this in some of my previous videos, and maybe I'll make a future video about it and discuss it from some different and more fundamental perspective. But yeah, here are just a few notes, just 2-page notes about the Schrodinger equation in general. After that, I have started deriving Schrodinger's equation for free particle using propagator, and this derivation is there, and then I have finished. This derivation is the last thing, and here I end this PDF. So yeah, where was I don't remember. It's page 50, I guess. Yeah, page 49. So we are currently we are at page 49, and we have 63 pages. Don't worry, we'll do it. We have come this far, right? So Schrodinger's equation is not an equation that can be derived in that sense. It's kind of guessed. Or it can be derived for special cases, although it is a general equation and it has been even verified experimentally. But it cannot be rigorously derived from any more fundamental principle. I mean, it is kind of a postulate of quantum mechanics. You cannot derive it from first principles. That is what I'm trying to say. It's basically a second order differential equation. I mean, it's second order in space and first order in time. And it describes the quantum particle. It is the law of motion in quantum mechanics. Just like in Newtonian mechanics, if you know the position of a particle and the forces acting on it, then you can calculate the trajectory of the particle using Newton's laws of motion. If you are given the forces that are acting on the particle and the initial position of the particle and the mass of the particle and everything, then you can do that, right? Similarly, this is the quantum mechanical law of motion, Schrodinger's equation kind of. If you know the Schrodinger equation basically gives the solution to the wave function of the particle, which we denote by this symbol, the Greek symbol psi. And psi basically contains all the information about the particle that is allowed in quantum mechanics. Why do I say that is allowed? Because in quantum mechanics, like uncertainty principle and all, there is some constraint. You cannot know everything with any arbitrary level of accuracy. That's why I say. Now, this psi or the wave function by itself has no physical significance. But again, mod square of psi is the probability of finding a particle at that specific position and at that specific time. So yeah, psi is a function of x comma t in general. In special cases, we also assume psi to be just a function of x. I mean, when the system is not changing with time, basically. So this was the Born interpretation, because see, basically psi roughly translates to the probability amplitude. Kernel or this propagator also probability amplitude, but there is a difference between the propagator and the wave function, which we will discuss just in the next page only. But yeah, this mod psi square gives the probability. This was the Max Born interpretation, and psi roughly translates to the amplitude of the wave describing the particle, and a wave, the amplitude of the wave can be negative, right? Wave is like this, the amplitude can be negative, but mod psi square is always positive, like I said, and yeah, of course, probability must also be positive, and if psi is normalized, then mod psi square will always be a value between 0 and 1, as we expect probability to be. So this is the basic form of Schrodinger's equation, that is minus h bar square over 2m del square psi over del x square plus v psi equals I h bar del psi del t. So m is the mass of the particle for which we are solving the equation, and psi is the wave function of that system, that particle, and del square del x square psi is the second order space derivative of psi, and we use the symbol del instead of d, the partial derivative, because here psi is a function of x and t, it's a time dependent Schrodinger equation. So that's why here you see in the RHS we have del psi del t. So it's the derivative with respect to time, and this is the first order derivative. Yeah, so I is the imaginary number here, and V is the potential. V is the potential. So this is the general form of the Schrodinger equation, right? And you notice one thing you notice is that this equation is first order time derivative in the RHS, and but it has a second order space derivative. But in special relativity, if you know, I mean, this is just a kind of extra discussion, this page. From here again, we are starting path integrals. But yeah, if you are interested, just listen, you can listen, it will take maybe maximum 2 to 3 minutes. So in special relativity, we know that space and time are on an equal footing. In Einstein's theory of relativity, in general relativity also, space-time continuum. Space and time are at an equal footing, right? It's not like so any equation which obeys both special relativity as well as quantum mechanics, they should not have a second order derivative in space but a first order derivative in time. This is not acceptable. But of course, this above Schrodinger equation, this form, it's a non-relativistic equation. It's a classical. I mean, classical in the sense, of course, it's a quantum equation. It's not classical. I mean, maybe I shouldn't write classical here. But it's non-relativistic because it doesn't take into account relativity. To derive Schrodinger's equation, we use the momentum operator and the kinetic energy operator, everything. But we use the kinetic energy form, we use half mv square or p square over 2m, the classical kinetic energy and everything. So in some sense, it does not take the relativistic modifications into account. But yeah, that is why I'm saying it's a non-relativistic equation. It does not take into account special relativity. Now, if both special relativity and quantum mechanics are to be reconciled, we need to address this issue, that first order time derivative but second order space derivative. Classically, kinetic energy is half mv square, I mean mv square by 2, and if we just multiply divide by m, we have m square v square by 2m. But mv is p, so m square v square is mv whole square, that is p square. So kinetic energy is p square by 2m, right? So it's proportional to the square of the momentum, p square. And yeah, momentum is mass into velocity, and velocity is proportional to the displacement x. So kind of it's proportional to square of x. I mean, this is not a mathematically rigorous argument, by the way, this part. I'm just trying to give an idea where this double derivative of space is coming from. Second order derivative in space is coming from. Because kinetic energy classically is p square by 2m. So it's proportional to the square of momentum. And momentum is proportional to mass into velocity. Velocity is proportional to displacement. So it's the square of displacement. But in special relativity in Einstein's equation, you see the energy is under root m square c to the power 4 plus p square c square. So due to this under root, you see, it's kind of you see it's energy is proportional to p, or it's and not the square of p. So Dirac reconciled special relativity and quantum theory in his Dirac equation, which predicted the existence of antiparticles. We all know these antiparticles, like particles which when if they collide with ordinary matter, they will just annihilate, and they have opposite electronic charge and some few other opposite properties as well. So this prediction was actually a theoretical prediction, but later it was verified experimentally. And this prediction came from Dirac's theory. Dirac actually, Dirac equation is the foundation of quantum field theory, which is a theory which takes into account both special relativity, the modifications demanded by special relativity, as well as quantum mechanics. Just an interesting discussion. I'll not discuss these things here in this video. Now last part is that deriving Schrodinger's equation for free particle using propagator. So I already showed you the Schrodinger's equation is h bar square over 2m del square psi over del x square plus v psi is I h bar del psi del t. And we have assumed this is in one dimension. That is why we are, if it was in 3 dimension, then it would be del square psi plus over del x square plus del square psi over del y square plus del square psi over del z square, which we together say the Laplacian operator nabla square psi. But yeah, here it's just one dimension, that is x comma t, one space dimension, and time is obviously there. Time dependent Schrodinger equation. This is time dependent equation, so time is always there. Now since free particle, there is no potential, so this Vx will be 0. Thus the equation collapses to the Schrodinger equation for the free particle collapses to minus h bar square over 2m del square psi over del x square is equal to I h bar del psi del t. So this is the equation which we hope to derive, the Schrodinger equation for a free particle. The same equation, except this term we ignore because V potential is 0 for a free particle. Now see, propagator and wave function. Propagator gives us the probability amplitude for a particle to go from one point to another, and wave function gives us the probability amplitude. It's also a probability amplitude, but it gives us the probability amplitude for a particle to be at a specific point in space time. Wave function does not care about the initial point. A wave function will only consider, okay, what is the probability amplitude for the particle to be present in this place, in this region of space time, in this position at this time. That is all the wave function cares about. Wave function doesn't care about where the particle came from, the initial point. But probability amplitude, but the propagator, as we have already seen, it takes care of both the initial point and the final point. Like it tells us the probability amplitude, gives us the probability amplitude for a particle to go from this point to that point. That is what I've written. Unlike a propagator, wave function does not contain any information about where the particle came from. That is the initial endpoint or the initial point. Wave function only cares about the probability amplitude for a particle to be present at the space-time point t comma x, denoted by psi t comma x. Now if we know this wave function psi t comma x or psi x comma t, it doesn't matter. See, psi in bracket something comma something means psi is a function of both of those things. So here psi is a function of both x and t. So whether you write psi x comma t or psi t comma x, that hardly matters. Yeah, when we are writing it in our, we usually denote these points the coordinates as t comma x, that's why, but it doesn't matter actually, just a notation. So yeah, so if we know this wave function psi t comma x, we can find the mod square of this psi, and to get the probability of finding the particle at the point t comma x. Now our goal is to derive a differential equation for psi t comma x, which is the Schrodinger equation. So we had derived this, that kba equals to integral dxc kbc kca, that is the multiplicatives of propagators. We have already derived this. Now let us replace the propagators by now see, kc comma a, let us replace by psi c. Why? Because a is the initial point and the wave function psi doesn't care about the initial point. So kc comma is the probability that the particle is at c. So we just replace it with the wave function that the particle is at c. Just forget about the a dependence. And similarly kb comma a, here also let us just forget about this a, and kb comma, let's write psi b. So so kc comma a is psi c and kb comma a is psi b. And but let's keep kb comma c as it is, because c is not really the initial point, right? It's an intermediate point, and we cannot just remove it from our equation like that. So now we can write from this equation that psi b equals to integral dxc kb comma c psi c. Nothing, just case in place of kc comma I have substituted psi c, and in place of kb comma a I have substituted psi b. So this is a wave function, this is also a wave function, but this is a propagator k term. Now let's see with the space-time point t comma y. See, here we only care about c and b, from c to b, and here psi c psi b, no a dependence. We don't care about a here. So let's see with the space-time point in this spacey x versus t plot kind of, and let's see with the space-time point t comma y. I mean, see, here y doesn't mean any the y dimension, the second dimension of space, not that y, that it's orthogonal to x, or I mean it's perpendicular to x direction, not that y direction. Here y is just x, it is the xc, the space variable at x that we denote by y for our convenience. I mean, it doesn't matter, you can write xc also, doesn't matter. And let the point at b, the space time, the c with the space time point t comma y, and the wave function at t comma y is psi t comma y obviously, and let b be the space time point t plus epsilon comma x, because a to c to b, I mean a to b and in between c. So a we have just forget about a, so c to b, that means b comes after c in terms of time. So C to B, the particle is moving from C to B, so B is slightly ahead of C in time. I mean, the particle will reach B from C at some later time. That is what I'm trying to say. In space, I don't know the particle is moving in what direction in space, that doesn't matter. But that is why we have defined the space time point B like t plus epsilon comma x. Yeah, this is y, that is x, or this is xc and that is x, doesn't matter. But time is t plus epsilon, it is epsilon ahead. Just here by epsilon, I don't mean that epsilon that we have divided into discrete times, just any arbitrary epsilon. Okay. So now we can write that this psi b equals to integral dxc k b comma c psi c. So we can write psi b equals to we can write, just a second. So psi b, now in place of psi b, we can write psi t plus epsilon comma x, because b is t plus epsilon comma x, and in place of psi c we can write this thing psi t comma y, and in place of k b comma c we can write k t plus epsilon comma x, because this is the point for b, the coordinates of b, semicolon t comma y, the coordinates of c. And this propagator k b comma c takes the wave function from c t comma y to b t plus epsilon comma x. Okay. Right. So now we rewrite, just a second, yeah. Now we rewrite this. So we had psi b equals to integral dxc k b comma c psi c. So now we can write in place of psi b, we just write psi t plus epsilon comma x equals to integral dxc. That means just dy, because xc is just y, this point. C, the x coordinate of c is y. Dy, then k b comma c is just k t plus epsilon comma x semicolon t comma y, we just now discussed, and psi c is psi t comma y. And this integration is obviously running from the limits are minus infinity to plus infinity, obviously, which I have not written time and again, but yeah, I already discussed. I told you that integration usually that means minus infinity to plus infinity, because we need to consider all the values of all the different x c's or all the different y's. So dy. Now the free particle propagator we derived was this, that k naught b comma a, or which is just this k tb comma xp semicolon ta comma xa. It's this thing, right? Under root m over 2 pi I h bar tb minus ta exponential this thing. So here we set tb equals to t plus epsilon, ta equals to t, I mean just as per using our notations, and xb equals to x and x equals to y. Doing this we get that k t plus epsilon comma x semicolon t comma y. Just this thing, in this thing we are just making this substitutions, nothing more. Then we get is equal to under root m over 2 pi I h bar epsilon tb minus, in place of tb minus ta we can write epsilon, right? Exponential im x minus y, because xp is x and xa is y, x minus y whole square over 2 h bar epsilon. See here tb equals to t plus epsilon and t is equal to ta. That means tb equals to ta plus, tb equals to ta plus epsilon I can write, because t is equal to ta and tb equals to t plus epsilon, so tb equals to ta plus epsilon. That means tb minus ta will be equal to epsilon, obviously, from these substituting equations only. So thus we now we have found an expression for k t plus epsilon comma x semicolon t comma y. This expression we have found. Now putting this k t plus epsilon comma x semicolon t comma y in this equation, psi t plus epsilon comma x equation, that means in this equation psi t plus epsilon comma x equal to integral dy k, in place of this k we will put this and then psi t comma y. So we get this psi equals to this thing under root m over 2 pi I h bar of epsilon, the constant we just taking it out of the integration, and then integral dy exponential this thing im x minus y square over 2 h bar epsilon and then psi t comma y. So here y is the integration variable and x is constant, because x is the end point. See, it's moving from y to x. X is the end point, so we will treat it as a constant, obviously. We want to find the probability amplitude at x. That is what we want to find, like psi. Now let us define a new variable eta equals to y minus x. So thus eta equals to if eta equals to y minus x, then y equals to eta plus x, I mean x plus eta, whatever. and since x is constant, then d eta will be just dy. Now we can just substitute. We can write that psi t plus epsilon comma x is equal to this constant times integration. Now in place of dy, let me write d eta because they're equal. And in place of, see that's what I've done, d eta, and psi this was what, psi t comma y. So psi t comma y, in place of y I have written x plus eta. So psi t comma x plus eta. At exponential I had I m x minus y squared over 2 h bar epsilon. I have just written that exponential I m eta square over 2 h bar epsilon, because eta is itself y minus x or x minus y. I mean x minus y square, if we just square it, or y minus x, doesn't really matter. And the limits of the integration are remain unchanged. See, when the integration was with respect to y, it was minus infinity to plus infinity. So eta is y minus x. So if y is minus infinity, eta is also minus infinity. I mean minus infinity minus x is minus infinity. X is finite, constant. And if y is plus infinity, then plus infinity minus some finite x, that is also plus infinity. So in that case, eta is y minus x is also plus infinity. So limits are unchanged. Limits are still minus infinity to plus infinity. And x minus y square equals to y minus x square equals to eta square. Yeah, this thing anyway. So now Taylor expansion, we all know about Taylor expansion. Taylor expansion of the function f of x about x equals to a. This is the simplest case for a single variable function. It is f of x at expanded about x equals to a. Taylor expanded is f of x at x equals to a. I mean the first term is just, we just evaluate the function by putting x equals to a. Then the second term is that x minus a into d, the first order derivative of the function with respect to x, that is df dx, evaluated at x equal to a. We calculate the derivative and then we put x equal to a. Then the second term is 1 over 2 factorial d square f over dx square, second order x derivative of the function evaluated at x equal to a and into x minus a squared, and then so on. The third term will be x minus a cube over 3 factorial d cube f over dx cube evaluated at x equal to a, and so on. Now for functions with two variables like f t plus epsilon comma x, suppose we treat here we have to treat one variable as constant, and we can expand it about the other variable. We can Taylor expand the function about the other variable. And since two variables, the rule is the same. Basically the rule is the same, but since two variable, we write in place of df dx or d square f dx square, we write del f del x, whatever. So here f t plus epsilon comma x, here we are treating x as constant, and we're expanding the t about we're expanding t this t about some point. So this is this will look of the form f t comma x plus epsilon del f del t. So see plus epsilon square by 2 factorial del square f by del t square. So basically epsilon is playing the role of x minus a here. I hope you understand. Epsilon is playing the role of x minus a. And epsilon corresponds to the x minus a terms. Now if we consider only up to first order term, that is we ignore this second order term, we neglect this, then we f t plus epsilon comma x is f t comma x plus epsilon del f del t comma x. That's all. Just the first two terms we take, because anyway I mean we can ignore in most real life physical scenarios, we can ignore the higher order terms usually because they become very small. If epsilon is very small, then epsilon square, epsilon cube, higher order terms and their differential, they can be ignored. Practically they can be ignored for all purposes. Now similarly, if we see here, it was the function was of the form t plus epsilon comma x. So here we treated x as to be a constant. Now if we want to Taylor expand f t comma x plus eta, now we will treat t as constant and expand this thing x plus eta. So then, but here we will retain up to the second order term. I will tell you why. You will understand why. But here we will retain up to the second order term. That is the first three terms. Like here we retain only up to the first order term. That's just the first two terms. So yeah. So anyway, using the same logic, f t comma x plus eta will be f t comma x plus eta del f del x plus eta square by 2 factorial del square f by del x square and so on. Here also eta plays the role of that x minus a. Yeah, whatever. Now we had this equation, right? That psi t plus epsilon comma x equals to this all of this into psi t plus x plus eta. So we know now we know the Taylor expansion of psi t comma x plus eta and also psi t plus epsilon comma x. So thus this equation it becomes in the left hand side psi t plus epsilon comma x, we take only the first two terms. So we have psi t comma x plus epsilon del psi del t is equal to, on the right hand side we have this thing under root m over 2 pi I h bar epsilon, then integration d eta exponential I m eta square over 2 h bar epsilon And then we have this thing psi t comma x plus eta. Here we take the first three terms up to the second order. So we just write it psi t comma x plus eta del psi del x plus eta square over 2. 2 factorial is 2 itself, right? Del square psi over del x square. So that means in the RHS, if we just break this, we have three integrations. If you notice nicely, this thing, the first term is with this psi t comma x plus this thing with the second term eta del psi del x, and then this thing with the third term plus this thing with third term, that is eta square over 2 del square psi del x square. So in the above equation, okay, now just a second. So I hope it's clear to you why, just a second, it's okay, I think we can maximum 4 hours. It's almost 3 hours 30 minutes right now, but anyway, it doesn't matter. Okay, so right now you see I think it's clear to the Taylor expansion. I mean, it's we have written it in a different form. Like here, usually we are familiar with this form x minus a, but here we have just written epsilon and eta. But basically, you see, if I write say x minus a is eta, suppose x minus a is eta, then what is x? X is a plus eta. Now, if I write f a plus eta, if I write x a plus f of x a plus eta, okay, let's say x minus a is epsilon, because in this page we have this epsilon, so it will be easy to understand. Let us say x minus a is epsilon, so x is a plus epsilon. So on the RHS we have f a plus epsilon. I mean on the LHS f a plus epsilon. That will be just f, then the f a plus epsilon evaluated at x equal to a. If x equal to a, that means epsilon is 0. X minus a is epsilon, epsilon is 0. So this is f a plus epsilon. So if epsilon is 0, that means the first term is just f of a. On the LHS we have f a plus epsilon. On the RHS we have the first term is f of a. Now come here. On the LHS we have f t plus epsilon. On the RHS the first term we have f of t. A plus epsilon a, t plus epsilon t. The same thing. And here we have assumed x to be a constant. X is the second variable. X does not change anything. It is just present in everything. Just comma x, comma x, comma x, and so on. So it's just a second variable, just because there are two variables, but the basic form is the same. Now f a plus epsilon, the first term is f of a. Second term, okay, df dx as usual, and x minus a in place of x minus a we will have just epsilon. See, epsilon df dt. I mean here it's t and here it's x, whatever. Third term, 2 factorial d square f dx square, fine. X minus a square epsilon square, because we have assumed x minus a to be epsilon. So and similarly eta for also. That is why I think this now it should be clear to you why we are writing it in this form, epsilon and eta. And this will be easier for us. Otherwise we could have written it in this form also, x minus a. But that is the thing, because in the LHS we have this our function of this form, t plus epsilon, x plus eta. So why not? I mean then we should write it in this form only, right? So anyway, we have on the LHS we have psi t comma x plus epsilon del psi del t, and on the RHS we have three terms, three integrations. And in the wave equation, this psi t comma x and its derivatives, like all this stuff, del square psi del s square, they are all constants, treated as constants, because the integration is the integration variable is eta. See, integration with respect to d eta. So eta is the integration variable in the LHS, all three terms. So we will treat everything else as a constant. And now let's look at the second term here. You see it's actually 0, because as I told you time and again, the integration limits are minus infinity to plus infinity. So it's kind of symmetric. I'm sorry, yeah. And since, see, now integration, see, del psi del x is constant. So just take it out of the integration. So we have integral e to the im eta square over 2h part epsilon eta d eta. So the function inside the integration is eta into e to the im eta square over 2h part epsilon. So this exponential term is even, because eta square. So even if we substitute eta with minus eta, the exponential term will not change. But we have a single eta in multiplied with this. So that means if I replace eta with minus eta, overall we will get a minus sign. And that means since the limits are minus infinity to plus infinity, we can say that using the properties of odd function, even function, we can say that this second term will be 0. Fine. So that is what I have written here. The second term of the RHS is 0. Now the first integral. Let's look at the first term. This constant integration d eta e to the im eta square over 2h bar epsilon psi t comma x. Psi t comma x is also constant, so forget it. Now e to the im over 2h bar epsilon, that means e to the some constant times eta square. Eta is a variable. So this is does it not remind you of Gaussian integrals? We discussed the general from Gaussian integral e to the minus x square dx integral e to the minus x square dx. So that is, we will be actually using a property of Gaussian integrals to evaluate the first integral actually. Okay. So we know that integral minus infinity to infinity e to the minus x square dx equals to root pi, the basic Gaussian integral formula. U be x over root 2 sigma. Sigma is outside the root anyway. Okay. So and then u square is x square over 2 sigma square obviously. And du, see, if u is x over root 2 sigma, sigma is a constant, then du is just dx over root 2 into sigma. And thus dx is equal to root 2 into sigma into du. So now let us say we want to evaluate this integral. Don't ask me why, you will understand. Let us say we want to evaluate integration minus infinity to infinity e to the minus x square over 2 sigma square dx. So then see, if we just make this substitution in place of if we just in place of dx, let me write du root 2 sigma. So see, sigma root 2 out constant out of the integration, and du in place of dx I have written du. Fine. And x square over 2 sigma square, you see this x square over 2 sigma square is nothing but u square. So we have integration minus infinity e to the minus u square du, and this thing sigma root 2 outside. So now this thing integration e to the minus u square du is just root pi, because yeah, integration e to the minus x square dx is root pi. X and u, they are just the different variable of integration, the same thing, right? So that means this is root pi. So we have sigma root 2 into root pi, that means under root 2 pi into sigma. So that means we have integration e to the minus x square over 2 sigma square dx is under root 2 pi into sigma. So now let's evaluate integration minus infinity e to the minus x minus a whole squared over 2 sigma square dx. Same thing as previous, but in place of x we have x minus a, that is just a shifted x. This is pretty simple. Let us assume y equals to x minus a, but since a is constant, then dx will be equal to dy, and limits are also unaffected because minus infinity and plus infinity. So then this integration can be written as, if we just put y in place of x minus a, we just have my integration e to the minus y square over 2 sigma square, and dx in place of dx we can just write dy because dx equal to dy. Now this integration we just evaluated is sigma and into root 2 pi. Whatever x or y, whatever, this is the same form. So we have this integration also, the value is the outcome is, the result is sigma into root 2 pi, right? So the first term in our equation, I mean in what we are doing is that, if you remember, it's this constant under root m over 2 pi I h bar epsilon into integration d eta e to the im eta square over 2 h bar epsilon, then psi t comma x. Again psi t comma x is constant, so this in the integration we have this integration e to the minus integration e to the im eta square over 2 h bar epsilon d eta. Now we want to express this in this form so that we can use this result sigma root 2 pi. So let us just compare. Let us say that minus 1 over 2 sigma square equals to im over 2 h bar epsilon. See, im over 2 h bar epsilon, because eta square corresponds to x minus a square or x square, whatever. Eta square corresponds to x that squared. So other than eta square, what we have in this argument of the exponential function, that is im over 2 h bar epsilon. And here, other than x minus a square, what we have is minus 1 over 2 sigma square. So we can say that minus 1 over 2 sigma square should be equal to im over 2 h bar epsilon, if we were to represent in that form. So if that is the case, in that case sigma will be sigma turns out to be under root I h bar epsilon over m. I mean minus 1 means I square. So this I cancel, and we are left with I h bar epsilon over m. 2 cancel, and that is sigma, and under root, so because sigma square. So if we can express this integration in this form and we get the value of sigma, then the result should be what? Sigma into root 2 pi. See, let us start with this integration d eta e to the minus eta square over 2 sigma square, and put sigma equals to this thing what we got here, under root I h bar epsilon over m, right? So then we get integral d eta exponential exponential eta square, and in place of minus 1 by 2 sigma square we are writing im over 2 h bar. So I eta square m over 2 h bar, and we already had I eta square, sorry, just a second. This is eta square. And then we have minus 1 over 2 sigma square, that is Im over 2 h bar epsilon. Right, so that means Im over 2 h bar epsilon. And we have eta square. Fine. Minus 1 over 2 sigma square and we have eta square. So Im over 2 h bar epsilon. Yeah, this is the same thing. I mean, I don't know why I have written I in the denominator, but yeah, this is the same thing ultimately. Because, I guess I have squared this sigma and I have this negative sign, I have substituted I square, but same thing, you can directly see that negative of 1 over 2 sigma square is equal to this, and here you have minus 1 over 2 sigma square, so you directly put this. Anyway, ultimately you get the same result, that I m eta square over 2 h bar epsilon inside the exponential, right? And that is what ultimately we have got, integration d eta exponential I m eta square over 2 h bar epsilon. Now, since we have used this value of sigma and we have expressed it in this form, we know that this must equal sigma root 2 pi, and here sigma is under root I h bar epsilon over m. See, here we have derived. So that means sigma root 2 pi will be under root 2 pi I h bar epsilon over m. We thus have in this integration, integral d eta e to the I m eta square over 2 h bar epsilon is equal to this thing, under root 2 pi I h bar epsilon over m. So this is just this integration we have evaluated, right? This integration. And outside the integration we have m, this under root m over 2 pi I h bar epsilon and psi t comma x. So the first term becomes this square root term, then psi t comma x into the integration, in place of which we are writing this result we obtained. But now you see the funny thing, you see the interesting thing. You see this term is under root m over 2 pi I h bar epsilon, and this term is its exact reciprocal, under root 2 pi I h bar epsilon over m. So they just cancel, and ultimately the first term reduces to psi x comma t, I mean psi t comma x, whatever. Right, now we are left to the last calculation for today's video. We now need to evaluate the integration in the third term. So let's quickly look at what the third term was. Second term is 0 already, we discussed. Now the third term is c, under root m, where was I? Yeah, under root m over 2 pi I h bar epsilon integration d eta e to the I m eta square over 2 h bar epsilon eta square by 2 del square psi del x square. Anyway, del square psi del x square over del x square, and this 1 by 2, they are constant, so they will be coming out of the integration. But still it's a bit difficult integration, because you have integration eta square e to the I m eta square over 2 h bar epsilon d eta. So we will use some mathematical tricks to solve this integration, right? So let's see, first let's evaluate 1 over sigma, just a second. Excuse me. So first let's evaluate this strange looking function, that 1 over sigma, sigma is a constant, 1 over sigma root 2 pi integration dx x square e to the minus x square by 2 sigma square. See, you can see some similarity, because in the third term, in the integration we have d eta square e to the minus some eta square something. So you can see the similarity. But how to evaluate this integral? It's not so straightforward, it's not so easy. So for this we define some function, a function of k, I mean phi k. We define this function like dx e to the I kx e to the minus x square over 2 sigma square. I mean, let's just define phi this way. We can define phi this way, right? No problem with that. And we're writing phi k because here essentially we will treat x as a constant, although we have, I mean not that, but we will take the derivative with respect to k, so we are just writing phi k. I mean yeah, so see, if you have like, now let's evaluate the second order derivative with respect to k of phi. So phi is dx e to the I kx e to the minus x square over 2 sigma square. So d2 phi over dk2, or the d square phi over dk square, I mean the second order derivative, will be equal to d square over dk square of this thing, this phi. I have written just phi. This is minus infinity to infinity. Actually phi is this integration. Okay, I'm sorry. Phi is this thing, integration minus infinity to infinity dx e to the I kx e to the minus x square over 2. This is how phi is defined. I forgot to put the integration sign here. Let me just do it here for you. Okay. A very bad integration sign, but okay, let me just try again, try one last time. Okay. Yes, that's loads better. So now there is d square over dk square, then this phi I have written integration minus infinity to plus infinity dx e to the ikx e to the minus x square over 2 sigma square. Now since the difference the integration is with respect to x but the derivative with respect to k only, we are just kind of, you know, we can just bring this d2 over dk2 inside the integration. So integration dx then del square over del k square e to the ikx, because the e to the ikx is the only term with a k in it, and then e to the minus x square by 2 sigma square, and we change the d to del partial derivative because now we are inside the integration, so x and k both are variables. Now, what is the second order derivative of e to the ikx? First of all, will be we are differentiating with respect to k, so I and x is constant. So the first derivative will be ix e to the ikx, and we need to take the derivative once more because second order derivative. So again ix will come out. So ix whole squared e to the ikx. Now what is ix whole squared? That is I squared x squared, and I squared is minus 1. So that is minus x squared e to the ikx. That is what I have written here. So this second order derivative will actually gives us minus this minus here, minus integration dx x square e to the ikx e to the minus x square over 2 sigma square. Now at k equal to 0, if we evaluate this result, at k equal to 0 there is only one k here, e to the ikx, and if we put k equal to 0 then this term just becomes 1. So then at k equal to 0 this we have minus integration dx x square e to the minus x square over 2 sigma square, and this is the integral we started with. This integral we wanted to evaluate. See, dx x square e to the minus x square over 2 sigma square, this is the integral we wanted to evaluate. So now it's a general result of the Gaussian integrals, that this I already discussed in this video previously also, right? That integration minus infinity to infinity e to the minus ax square plus bx dx is equal to under root pi over a e to the b square over 4a. This I discussed when I was talking about the general form, the results of Gaussian integral. So you can prove this also. The proof is a bit mathematically involved, but you can do this. But then that's not relevant here. I mean, some things you have to assume. This is Gaussian integral, right? I mean, it's not assume. We know this is true, but yeah, maybe you did not get the satisfaction of knowing the exact proof right now, because I myself don't remember the proof of this particular formula right now, and I don't want to make the video any longer, to be perfectly honest with you. So setting a to be 1 over 2 sigma square and b to be ik, both of them are constants obviously. Then we get integration e to the minus ax square. So e to the minus x square over 2 sigma square plus bx, that is plus ikx, because b is ik, dx. And e to the a plus b can be broken up like e to the a into e to the b. So that means this can be written as integration e to the ikx e to the minus x square over 2 sigma square dx. Now this is phi k. That's see, we defined phi k to be this integration e to the ikx e to the minus x square over 2 sigma square dx. See, e to the ikx e to the minus x square over 2 sigma square dx. So this is phi k. Now that means phi k we can be written in this form if a is under root, if a is 1 over 2 sigma square and b is ik. So that means this is equal to root pi over a e to the b square over 4a. So that means pi over a. So a is what? 1 over 2 sigma square. So 1 by a is just 2 sigma square. So we have under root 2 sigma square pi, or sin sigma square. So sigma root 2 pi. This is what we have. And e to the b square over 4a. So what is b square? B is ik. So b square is I square k square, that is minus k square. So if e to the minus k square divided by 4a. A is 1 over 2 sigma square, so 1 by a, that means 2 sigma minus 2 sigma square k square over 4, and if we just cancel 2 and 4 we will have e to the minus sigma square k square over 2. That is what we have here. So thus phi k is we have evaluated this integral phi k, and that is sigma root 2 pi e to the minus sigma square k square over 2. Now we also proved just now that if we take d2 phi over dk square and we evaluate this at k equal to 0, then we will get that our original integration. So let's find d2 phi dk square first. So that means the ddk of ddk of phi, that means ddk of this thing, sigma root 2 pi e to the minus sigma square k square over 2. So that means ddk of if we take the first thing, sigma root 2 pi is constant, then into minus sigma square over 2 comes out e to the minus sigma square k square over 2 into 2k, because k square, that is 2k, right? Now one more time we need to differentiate whatever we've got, because second order derivative ddk is here. So that means okay, so these 2 and these 2 will cancel out, and sigma root 2 pi will come out because it's constant, right? And we have a minus sigma square here. Sigma is a constant, so this will also come out. So minus sigma cube basically, because we have a sigma here. So minus sigma cube root 2 pi. And now we have this outside the derivative, and we have ddk of this k here and this e to the minus sigma square k square over 2. Now it's a derivative of two terms, two functions, k and this exponential term. So we need to use the product rule. So first is that yeah, minus sigma square root 2 pi, the constant outside. First we derivative with respect to k, and that means we treat this as a constant. So it's a constant e to the minus sigma square k square over 2, and ddk of k or dk by dk, that is just 1. So the first term we have taken care of. Second term we have to take the derivative of this exponential term and treat k as constant. So that means we have minus sigma cube root 2 pi k and ddk of this thing. Now what is ddk of this thing? That is again 2k. 2k will be there, right? And then we have minus sigma square by 2. So 2 cancel. So we have a minus sigma square here. And we have a minus sigma cube here. So we have sigma to the power 5 here, plus sigma to the power 5. Sigma square and sigma cube. Plus sigma to the power 5. So far so good. Okay, and 2 cancel, and we will have a k here also. So this is where this k square is coming from, because see, you have sigma to the power 5 and we have root 2 pi, fine, perfect. And this k we treat as a constant, because now we are dealing with this term. So this k is there, but while dealing with this term also we have a 2k. The 2 gets cancelled with the 2 in the denominator of this minus sigma square by 2, but the k remains. So 2k, that means k square, and then we have this e to the minus sigma square k square over 2. So that means if we take sigma cube root 2 pi e to the minus sigma square k square over 2 common, we have from this term we have plus sigma square k square, because sigma to the power 5, and sigma cube common, so sigma square and k square from here. And from this term we have just minus 1, because this entire term we have taken common. So this is this second order derivative. Now at k equal to 0, this term will be 0, minus 1 will remain, and this term will also be 0. I mean this term will be 1. K equal to 0 means yeah, k equal to 0 means 0, so e to the 0 is 1. So we will be left with just a negative sign from here and negative sigma cube root 2 pi. That's all. Just 3 more pages. Okay, we are already at page 61. So now since integration, so we derived that this I mean what I was saying. Yeah, so I derived that yeah, this one I'm talking about. Initially only I derived that d2 phi by dk square evaluated at k equal to 0, that is actually negative of this integration dx x square e to the minus x square over 2 sigma square, right? So negative of this integration dx x square e to the minus x square over 2 sigma square, that is equal to d2 phi by dk square. Actually this is d2 phi by dk square at k equal to 0. I have not I forgot to mention that here. At just a second. Quickly let me do this. I mean it's pretty very worse handwriting, but anyway I hope you'll understand. So and we just evaluated this integration. I mean we just found out the value of phi as you can see here. Because phi was the integration, and we expressed it in this general form, and we use this formula to find the value of phi, and we evaluated the d2 phi by dk square at k equal to 0, and we got minus sigma cube over 2 pi, and this should be equal to this integration, right? So minus minus cancel, so we have sigma cube over 2 sigma cube into 2 pi, sorry, sigma cube into 2 pi, not over. So sigma cube into 2 pi is equal to integration dx x square e to the minus x square over 2 sigma square. This is what we got. Now if we divide both sides by sigma into root 2 pi, we will have 1 over sigma root 2 pi into integration dx x square e to the minus x square over 2 sigma square, and on the right hand side we will have simply sigma square, because sigma cube over root into root 2 pi, so divided by sigma into root 2 pi, so just sigma square will remain. Now in terms of eta, I mean if you just substitute x to eta, just variable change, I mean not even a change, just change, so writing the same equation in terms of eta, we will have 1 over sigma root 2 pi integration d eta square e to the minus eta square 2 sigma square is equal to sigma square. Right, and now we will put sigma equal to under root I h bar epsilon over m, just like we did in the previous case. In the previous, in the previous case we did not do this, right? This in the first, when we were evaluating the first term, I think we did something similar, right? Yeah, in the first term also we put sigma equals to this. I mean, we put means we actually derived from the Gaussian form, general Gaussian form, that if minus 1 by root 1 by 2 sigma squared is y m over 2 h bar epsilon, then sigma should be this, right? See, you see the first term and the third term, if you notice, if you notice properly, this inside the exponential function is the same thing. Only this is, here we have a eta square, extra eta square to deal with, which is giving rise to all these complications. Otherwise, they're the same thing, right? So that means, just a second. Yeah, we can write this. Now we put sigma equals to I h bar epsilon over m under root. Why? Because we can do, from there we are getting, I already told you. So then we get the third term, is this thing was constant outside. I mean, no, we are not yet reached there. Okay. So we are just dealing with this term. So if sigma is under root 1 h bar epsilon over m, then 1 by sigma root 2 pi will be equal to under root m over 2 pi I h bar epsilon, clearly. And then we have this integration here, d eta square exponential, okay, exponential minus eta square over 2 sigma square. So sigma square is I h bar epsilon over m in that case. So exponential minus m eta square, because 2 sigma square. So okay, 2, yeah, m will go to the numerator, and minus m eta square over 2 I h bar epsilon. Yeah, makes sense. And then in the next step I have just done nothing. I have just shown this, okay, you know, that here minus, if we write I square, then we can cancel the I in the denominator, and we will have exponential I m eta square over 2 h bar epsilon. And this is I h bar epsilon over m, or sigma square. I mean, this was equal to sigma. See, this equation you see, this was equal to sigma square, right? So, and sigma is this, so sigma square is I h bar epsilon over m. So, this is a valid equation, that this thing is equal to I h bar epsilon over m. Now, you see the third term. Third term was under root m over 2 pi I h bar epsilon. See, under root m over 2 pi I h bar epsilon. Integration d eta square, integration d eta square by 2. We have a by 2 yet. So, that is we will deal with that. And del square psi del x square, which is a constant anyway. So by 2 and this thing we don't have, but otherwise you look at this term, e to the I m eta square over 2 h bar epsilon, the same thing, e to the I m eta square over 2 h bar epsilon. So we have evaluated this integral, and it is I h bar epsilon over m, right? I mean, so this entire thing is this. So if we just want to find out this integral, so we need to take this under root m over 2 pi I h bar epsilon to the right hand side, and then we will get I h bar epsilon over m to the power 3 by 2, because I h bar epsilon over m to the power 1 we already have on the right hand side. And from here, if we just bring it to the right hand side, we will have I h bar epsilon over m under root, that is to the power half, and 1 plus half is 3 by 2. So this is 3 by 2, and 2 pi here, there is only 1 2 pi here, so if we bring it to the RHS, we will have just under root 2 pi. So third term in our equation was this, and so just if we just take this 1 by 2 and del square psi over del x square outside, because they are constant, we are left with this. And this thing we just evaluated is what? Is this thing, I h bar epsilon over m 3 by 2 root 2 pi. So that's what I have written, root 2 pi into I h bar epsilon over m 3 by 2. And here we have 1 by 2 del square psi del x square, no problem with all of this, and m, yeah, this thing. So this root 2 pi and this in this term root 2 pi cancel, and I'm left with under root m over I h bar epsilon to the power half, that is under root. And here I am left with I h bar epsilon over m to the power 3 by 2. So let me just break it. I h bar epsilon over m to the power 3 by 2. That means I h bar epsilon over m to the power half, which I have written here, into just simply I h bar epsilon over m. So this and this cancel. Both of these are under root term and they are just reciprocal. So they cancel. That is why I did this. So I am left with I h bar epsilon over m into just this, into half into del square psi over del x square. So that means we have I h bar epsilon over 2m, see I have epsilon over 2m, because we have a half term here, del square psi del x square. This is the third term. Now note that although we in the third term, in the integration of the third term, we actually have a second order space derivative, del square psi del x square, but we still end up with a equation which is linear or first order in terms of time. Time means epsilon here, obviously, right? So note that although we started with the second order derivative in space variable x, we end up with an expression that is first order in time. It's first order in time. Epsilon. Not there is no epsilon squared term or anything. Basically, we only consider terms up to those linear in time. That is why in this case, in the Taylor expansion, we took the first three terms. But in that case, in the time case, we took the first two terms because that was about time itself. So if you took the second order, then it will the result would be second order in time, right? So putting all the results together, we get, so let's look at this equation first. Let's go back to this equation, okay? So in the LHS, we have psi x comma t plus epsilon del psi del t, nothing more. That's what we have in the LHS. Psi x comma t plus epsilon del psi del t equals to three terms. Second term is 0, forget it. First term is just psi x comma t. And last term is, we got something I forgot, just now I showed you. Yeah, last term is we got this. I h cut epsilon over 2m del square psi del x square. So putting this together, we have in the LHS we have psi x comma t plus epsilon del psi del t equals to the first term psi t comma x plus 0, the second term, plus the third term is this. Yeah, I h bar epsilon over 2m del square psi del x square. So this psi x comma t cancel from both sides, and epsilon also we can cancel. See, here we have epsilon, here we have epsilon. So we have ultimately del psi del t equals to I h bar over 2m del square psi del x square. Now if I multiply by I h bar in both sides, in the LHS will become I h bar del psi del t, and the RHS will become, we multiply by I h bar. So we already have I h bar, that means I h bar whole square, that means I squared h bar squared. I squared is minus 1, that means minus h bar squared over 2m del square psi del x square. Now see, this is the Schrodinger equation for a free particle. If you can recognize, if you can recall, I h bar del psi del t is equal to minus h bar square over 2m del square psi over del x square plus v psi. That was the Schrodinger equation, but for a free particle v is 0. So this is the Schrodinger equation for a free particle, which we have successfully derived using path integrals. So now I would like to, it's exactly 4 hours. Now I would like to finish this video. I discussed a lot of interesting and mathematically heavy but a technical but useful and interesting concept, I hope, and I hope I made made the point. I hope I could give you at least a basic idea, even if you did not understand each and every nitty-gritty details. I hope I gave you a basic idea about path integrals, and that is the main thing. That is what I want. That is what we all want. If you're just watching a video of path integral for the first time, it's not expected that you will understand everything at one go. Even I did not. And anyway, it's a very pretty advanced topic for my age, and for anyone, even for PhDs in physics. Path integral is the mathematical techniques we use and the mathematical elegance. It's beautiful but advanced topic, but advanced and very difficult topic also. You need a lot of time to get a grasp of it. Okay. But anyway, so I hope that was the point of this video, basic introduction to path integral, and for the free particle case, we derived the free particle propagator very rigorously, and we used our result to derive Schrodinger's equation for a free particle, de Broglie relation for a free particle, as well as Planck's equation, Planck's quantum equation for a free particle. So yeah, that's all guys for this video. I don't want to I'm feeling really tired. If you can see the screen, it's 4 in the morning. On 4 a.m. So I don't know. Let me get. I have some stuff to do as well, some journal stuff as well. I have some articles to edit and some a lot of emails to reply and stuff. I think I'll do it now only, and after that I'll sleep. My sleep schedule is really messed up in general. Plus now the holidays are going on, so it's more messed up. But anyway, I feel satisfied that I completed this video in the end, and I didn't pause even once in the middle. So yeah, it's a 4-hour long video. My record is still that modular symmetry video that was 4.5 hours, 4 hours 30 minutes. But yeah, this is also the second longest YouTube video I've ever recorded, 4 hours, 5 minute path integral. So yeah, anyway, that's all guys. Thank you very much. Thank you very much guys for watching. And if you and comments are welcome. If you would like to comment anything, please do so. Thank you. And I hope this was useful. Thank you.